right, so without further ado, you should be able to see the screen there. Um, is a overall agenda. So I'll give a brief introduction and overview for the program, particularly for those that aren't familiar with it. Some of the stuff that we've done in the past, and we can provide more details on those with previous reports and presentations. And then we'll really jump into the meat of what we want to cover today, which are our research task reports. And this will be a mix that will include both faculty and students reporting on the three general areas that we've been focused on, including observations, predictions, and implementation. This won't cover everything that we're doing, but this will cover a large part of it in terms of what we've been not only accomplishing over the last year, but also an overview of where we're going in 2023. We'll finish up talking a little bit about outreach, some of the outreach aspects that we've been working on, and then end with a discussion on our 2023 campaign plans. Now, this is a very broad coalition of partners, universities, NCAR, through the FFRDC, and then industry partners, which includes both Vigilant Aerospace Systems and recently onboarded Climate Vision, as well as the Choctaw Nation of Oklahoma through the FAA Beyond Test Site. And all these partners have been really instrumental in pushing our goals and objectives forward. This really has been a true team in terms of not just siloing the different tasks that we've had at each of the universities, but really reaching across, not only the university, but state boundaries, in working with all the members across the team and being able to bring in other components as well. You'll see throughout the presentation that there are a number of partners that are working outside these as well. These are our great team members, our leaders of the effort. We don't have a picture here of all the students. That's something that I'm behind on in terms of being able to pull that together. You'll see some of the students today, but if you think about each one of the investigators here having, one or two, and in some of the cases, 4 or 5 students, you can think about the broad reach that we have in terms of the number of folks we have working on this effort. And we understand the complexity of the problem, but also the importance, and it does take, quite a large team to be able to pull off all the tasks and efforts that we're looking at. So we did take opportunities. We talked about this at our last quarterly meeting to focus on some in-person opportunities. So in addition to the in-person Weather Technology Forum that we held in Tulsa, Oklahoma last fall, we've had the opportunity to be able to connect with team members both at AGU in December and AMS last week, and then upcoming in AIAA in DC next week. So we had a number of presentations that were focused on the WINDMAP effort presented at AMS last week in Denver, and then we'll have several papers that will be presented at AIAA. If I don't have yours represented here, please let me know. So that way I can make sure to get you included on this list, because we will send out a comprehensive list afterwards as well. I know there'll be a number of us that will be at AIAA next week. So just let me know if you'd like to get together so that we will have an opportunity to meet up in person. I would like to, I know Grady, you mentioned Tyler's work. Tyler was an undergraduate student here working on WINDMAP as part of her senior design project. So she has since moved to NASA Langley and has been working with the Virginia Tech team. So again, I think that's a great example of showing the serendipitous nature of all the effort that we've been doing. I would like to bring this up. We talked about this last year. We didn't get quite things pulled together to be able to put a WINDMAP specific session in AMS or SciTech this year. But since we'll be coming up on the 4th year of the program next year, this will be a really good opportunity to highlight all the work that we've been doing. So we will have plans for both AMS and AIAA WINDMAP focus sessions at next year's events. So just for your, for planning purposes, AMS will be in Baltimore from January 28th to February 1st next year, and SciTech will be back in Orlando at the Gaylord, of course, from January 8th to the 12th. In 2024 as well. Now, James and I are both serving on the ARAM committee at AMS, and I believe we have Matt Franzak on here as well, our erstwhile leader. So we will have a capability to be able to pull a session together for that. So I'll be working with those that would be interested in giving presentations, so that way we can get all those submitted. We will be working, since I happen to be the chair for next year's meeting, on getting some of these session topics put together this spring. I know that we'll be starting to do that next month. So this stuff will be happening pretty quickly. Suzanne and I are also serving on the Unmanned Systems Committee at SciTech. So we'll be able to have those discussions in terms of pulling together a session dedicated to WINDMAP at SciTech as well. So we'll be able to talk about that next week. And if you have anything to add on that, Suzanne, just let me know. Or James or Matt on AMS. I did get word from Joachim Reuter last week at AMS that they do plan on holding ASARA this year in 2023. Rather than Andorra Space, which opened up a lot of logistical problems last year, holding this in Bergen this coming August. So once those details are finalized, I'll make sure everyone is aware of that. So for those of you that would be presenting not only your other research, but WINDMAP related research at ASARA this coming year, that will be a good opportunity to do that as well. Okay. Any comments on this, the things I may have missed from our team? Okay. Now, really quickly, again, I don't want to go into this in a lot of detail because I think most people, even our guests, are already familiar with what our goals are. It is really focused on filling those gaps in the mesoscale and microscale data and forecasting capabilities by providing better observations, assimilating those observations into the high resolution forecasts, and then pushing those forecasts and real-time reporting out to the aviation community. So this requires coordination between those three different elements: the observations, the prediction, which requires that data assimilation component, and finally the implementation piece. So development of this concept has been something that's been around for quite some time, but obviously there are a lot of nuances and complexities in terms of making this actually work. And we are convinced that if we can do this correctly, that will significantly enhance not only real-time reporting and forecasting capabilities, but also the safety and efficiency of the entire air transportation system. Now, this is really based upon our experiences that we've had as a team in terms of using UAS and understanding what the needs are for enhanced weather information to be able to operate these systems in the NAS, but also then simultaneously utilizing these systems in providing enhanced weather observations, because we can get a lot of good data off these systems as they're operating, whether they're dedicated weather observation platforms or whether they're really just focused on doing some other mission, whether it's remote sensing or delivery, and then being able to couple these systems together. And of course, there's a lot of movement in the aviation weather community in determining what these needs are to be able to operate these systems in a much broader context. While we're specifically focused on UAS, primarily because that's not only our background and expertise, but also that's where the cost of the program makes the most sense, is using these much smaller systems. There's a lot of direct applicability to the advanced air mobility system or urban air mobility capabilities at large, and even eventually standard ATC operations for things such as icing, downburst, and shear prediction near airports. Now, while the goal is being able to focus on the urban canopy observations, I always like to pull this picture off. This is from Dallas a few years ago. Brian and I were actually flying from Stillwater down to Dallas this day, where we were socked in about 6 hours due to unpredicted and persistent fog layer that sat over DFW. And this is always a great example of the issues concerning AAM operations, particularly in urban areas, in terms of being able to navigate not only visibility, but also high wind issues. So the goal being able to not only map out the atmospheric boundary layer outside of urban areas, but also this urban boundary layer and the urban canopy that we have, and then taking this data to be able to improve our models is really the goal of the program. And I think you'll see, particularly with what we've been able to do on both the observation and prediction side, that we're making great strides in moving the ball down the field, allowing us to be able to predict not only a lot of wind specific, but also a lot of weather specific cases that really are very complex and difficult to do at the current time. Now, we have separated this into three different focus areas. The first of those is observations, being able to take these new entrants into the national airspace, utilize those to increase our sampling within the atmospheric boundary layer, take that data, assimilate it into novel high-resolution models, and then push that information out to the unmanned traffic management system to be able to improve the safety case. So the presentations today will focus first on the observation work that we've been doing, and then transitioning over into the prediction side, including both data assimilation and numerical weather prediction. And then finally, our industrial partners will talk about the implementation work that we are currently doing. Now we do have, I won't go through these in detail as part of the ULI program. We developed both milestones and progress indicator charts, or predicting what those capabilities would be in terms of advancing the TRL related to each one of these areas, primarily technical challenges related to development of autonomous UAS capabilities to conduct these observations, to be able to improve the data assimilation and forecasting, and then finally integration of the systems into the unmanned traffic management network. So these are things that we keep track of and that we update based upon where the objectives and deliverables of the program are currently at. So I'll pause there for a second to see if there are any questions from any of our guests. And as I wait a minute to see if there are any, I'll give you a second for those of you that will be presenting to situationalize yourself with the order of operations for today. Okay. Without further ado, then we'll go ahead and get started with our first set of presentations. So I'll turn that over to you, Sean.
Thanks, Jamie. We can go ahead to the next slide. So our team has changed a little bit over the last couple of months. We lost our two graduate students, Sam Keever and Margaret Bush, to industry. Sam went off to GE Aviation, and Margaret into Mitsubishi Automotive. So we have a couple of new students that have joined the team. Pretty much in the last semester, they're still kind of learning the ropes and getting on board with their projects. So I'm going to be covering most of the presentation, or I'm going to be covering the presentation of their work today and what they'll be doing. In sort of a big picture, what we're trying to tackle are basically three aspects of the project. One of them is looking at how representative profiles from rotorcraft UAS are when it comes to spatially complex terrain and topography. So this would be relevant in particularly the urban canopy when you have a single aircraft that's doing a measurement. What's the errors that are associated with that measurement due to just the complexity of the surroundings. So this is meant to kind of feed into the work that NCAR is doing with their data assimilation work, and we're looking towards kind of building error bounds that would then be going into their simulation. And then feeding into that is in order to get good measurements from a rotorcraft. One of the challenges with rotorcraft is getting flux measurements of momentum, latent heat, and sensible heat flux. mostly due to the rotors themselves. So we've been working at a new configuration for multi-rotor UAS. And I've recently touched base with Adam Houston at Nebraska, that suggesting that some of the work that we've been starting, looking at the flow field around a rotorcraft, could be of use to them as well. So we'll be coordinating more with them as we move forward with that. And the last little bit is kind of a new piece that we're starting up now, where we're looking at droplet size measurement using UAS. And this is something that we look to coordinate with OSU with in some of their cloud-based measurements they're proposing to do as well. All right, next slide, please, Jamie. So the first slide is just presenting some of the plans and previous work that we've done on the complex terrain. So early in the project, we did measurements in eastern Kentucky, and we developed an approach that kind of let us look at kind of the variability of the distribution of pressure, temperature, winds, humidity, based on spatial distance. So this is kind of leading towards the concept that we can build a summation of errors that we could then identify certain characteristics that might increase that or alter that distribution. And then that would be related to the time step and the spatial cell size of the numerical simulation. So last summer we continued with that work. One of the things we wanted to do was try different types of terrain. So we went to a place near Versailles, Kentucky, where we did a series of measurements over several different days, so at different points in the summer, where we did those spatial measurements over right near the Kentucky River, which has a very sharp canyon-like surroundings, which would be potentially similar to what you might see in a more urban environment. And then we did distributed measurements with rotorcraft or with fixed wing UAVs, and some vertical profiles with rotorcraft UAVs. So this was Sam's work. We were able to get the data, but we're now in a point of transition. So it's now up to me to actually continue with his analysis. So we've slowed down on that front. So hopefully I'll be able to pick that part up again soon and get this analysis in, and then we'll be able to keep going with this work. Next slide, please, Jamie. All right, and this is something that Margaret had been working on. So we've been working with kind of as James Pinto described it, a halo arrangement of sonic anemometers around our rotorcraft in order to get those vertical fluxes. And the idea is that we're out of any influence of the rotor wash with those measurements, which are going to let us back out the vertical component of velocity, which is the challenge for these types of aircraft. We've done numerous measurements with this aircraft. We're pretty confident that we're getting decent vertical winds from it. So the next step was to conduct some computational fluid dynamics in order to kind of verify that our position and wind field was clear of the rotor wash, and then get a sense of really how to adjust how we integrate the measurements from those three sensors. So see if we can refine our algorithm a bit more. So this work is still in its infancy, at least the CFD part is. You can see some of the preliminary results on the left, and there's a lot of cell distortion right above the rotor wash, and so we were looking at refining the mesh a bit. So Garrison is going to pick up with this work and hopefully get some good simulations. At that point, we'll start looking at the effects of side winds, and vertical ascent and descent rates, and see how that affects the wind field surrounding the aircraft, and where there might be ideal sensor placements, and potentially, if necessary, bias corrections that we can introduce. Next slide, please, Jamie. All right, and this is our new effort. This is kind of arose. We were at a conference last November and saw several talks that kind of reminded me that we can use hot wire probes to measure droplet size. So hot wire probes are they're usually used for turbulence measurements. They're very fragile, thin wires that are heated up to a relatively high temperature of a few hundred degrees Celsius. But one of the benefits is they have very fast response in the order of 40 kilohertz or so, depending on the sensor. But one of their challenges is that since they're really a heat transfer measuring device, if they're impacted by say water droplets, it's going to change their heat transfer, which makes them difficult to use in conditions of fog or clouds or that sort of situation. But there have been years ago, there were studies that looked at actually using that influence of those droplets and backing out the signature left by the droplets in order to determine the size of the droplet that hit the sensor. So this is that's the center middle portion of the slide, I guess, which shows some of their results. And it so happened that years ago we did a series of flights with a hot wire probe, and it started to rain partway through the flight, and we actually had captured some signatures of the droplets hitting the probe. So that's what we're seeing on the lower left there. And all those little spikes, those are individual drops. But if we zoom in on those drops, so center bottom, we can then see the response of the probe to each individual drop. Now, the difficulty is that our signature does not look like the signature that they were looking at in this 1970s paper. The reason for that, I think, is that our hot wire setup had a much higher response. So it's actually, instead of being an underdamped or an overdamped response, it's more of a critically damped response. We get the sort of second order response. So what we're trying to now do, what NISA has been working on, is modifying kind of the response model to see if we can now adapt the previous efforts to see if we can figure out what size of drops we're hitting our probe. So that's what we're seeing on the right, is kind of these two sorts of estimates of droplet size, and the nice thing is that what we're seeing is within the range for raindrops. So that's great, but the problem now is that we don't actually know what the size of the raindrops were that hit that particular flight. So the future goal for the effort is now to conduct some more controlled studies. So we're going to actually get a mono-dispersed droplet generator and put that in the wind tunnel and see if we can adapt our models or calibrate and tune these models in order to get the droplet size. And then if that works, then we will try and join OSU for their in-cloud flights that they are planning hopefully this year. I think that's it for me, Jamie. Thank you.
Thank you, Sean. Yeah, I find that this last piece in particular really interesting. I think this is, could be very impactful for the measurements, particularly with the high spatial or high temporal resolution that we'll get out of this. What size of hot wire are you using currently?
We use 0.5 millimeter, so 2.5 micron diameter, 0.5 millimeter platinum wires. So part of which could influence our ability to pick out droplets, but that might be okay for clouds. Rain might be difficult because the raindrops are going to be larger.
Yeah, Yeah, I'm wondering even right, you could have two or more probes of different diameters to be able to do a discrimination between those. But this is really interesting.
Yeah, there'd be a weight issue because the anemometers themselves are pretty heavy, so we start getting more than one probe.
Oh.
We
Do we
can
have
just
any
put it
other
in a bigger
questions?
plane.
Do we have any other questions for Sean?
Hey, Sean, this is James. I just had a quick question. It seems like you could also possibly derive, I guess, a couple of things, the water content and maybe in supercooled clouds, something to do with the icing rate, possibly.
So water content of the air,
Liquid water, so condensed water.
condensed water, potentially. So the what we're picking up is this sort of enhanced heat transfer from the droplet kind of hitting the wire and then adhering to the wire. So
Oh, it actually adheres to the wire.
yeah, surface tension will keep adhering. So what that sort of in the top middle picture, what you're seeing is the initial spike of the water hitting the droplet, hitting the probe, and then because the probe's at a few hundred degrees Celsius, that drop burns out really quick, right? Vaporizes really quick. So then that's the tail off, and then that's how you figure out the droplet size is how quick that tail is. So I'm not too sure if there's what we'd see if there wasn't a physical drop to impact the wire.
Right. No, it would be condensed. So I guess you would just have to integrate the drop size distribution to get the water content.
Oh yeah. We can. One of the things that I'm looking forward to seeing is some of the drop size distributions. Yeah.
Cool.
Okay, moving on to Brian.
All right. Yeah, you can go ahead and go to the next slide. So, kind of looking at the agenda, I realized I probably should have expanded this. So I prepared these slides primarily on what Trevor Wilson has been doing, but I'm thinking I should probably include Braden in the future because they kind of go hand in hand. Braden is looking at measuring in urban environments, so around different buildings. While we've been focused more on a direct comparison between a clean tower and a drone nearby, and then trying to expand that out to look at turbulence correlation parameters, purely from drones ultimately. But so last year we published a paper, partially on lab work, but most of our analysis focused on comparing the turbulence statistics from a tower versus a drone. And it turned out quite well, except for there was clear bias during some periods between the tower and the drone. We suspected that it was due to a lack of accuracy in the position of the drone relative to the tower, and B, the local shear conditions. And so this year we were, we'd hoped to run in several other locations, but some of that data we weren't able to collect. But this was one run from earlier this year. And the time trace there shows the drone, a mass, and then we had a ground station to get an estimate of the local shear. And yeah, you can go to the next slide. So ultimately the goal was to resolve some of those issues, but right away in the spectra, so on the left was from the journal article, which the spectral slope matched quite well between the mass, which was the dashed lines here, and the solid lines that were measured from an anemometer on the drone. But then if you look at this year's, where we are being, I would say, more careful on some of the details. The slope is different, and so when we're ready to take a step forward, the results actually look a little bit worse. So I think our next steps are, well, we're forming a full test matrix to basically improve resolution. And there were some concerns about the orientation relative to the wind direction for this test. So, I mean, at this point, I think we are aiming at just expanding the observations to kind of resolve some of these questions. And then what I don't have slides for that I should have is we're having Braden go ahead. He's put together a test matrix that isn't just for our stuff, where we'll compare, like move on to like 2-point correlations between drones and fixed towers. But he'll also start mapping out the complex flow field around buildings. Oh, you did have that. Oh, sorry, Jamie. I didn't. Were you going to present this?
I got too clever, Brian.
Oh.
So that was later, but I'll come back to this if you want to go ahead and talk about
no,
it
no,
now.
no. That's fine. I just looked at the agenda and I was like, oh no, I didn't see where you would be presenting it.
Yeah, this
I
was
mean,
primarily for the urban campaign discussion later, but I think it's relevant
Okay.
here if you want to talk to it.
I mean, I was just making sure that I was going to get. So yeah, we've been working with Braden on making these plans. I mean, you prepared these slides, so
Yeah. These are really just preliminary observations at this
Yeah.
stage, but they're go hand in hand with prep for the other urban field campaigns.
Yeah, and we're trying to leverage our effort to gain confidence for his measurements. I think that's really the main connection between the two, and working closely with him and his planning. I would just push that to where you originally planned it. Yeah.
Thanks, Brian. Do we have any questions or comments for Brian? All right, moving on to Carrick. I believe we're having someone present for Carrick this morning.
Are you able to hear me, Dr. Jacob?
Yes, I got you now.
Okay, excellent. I had to switch microphones. Yes, Dr. Delara is actually in a meeting right now, at conflict and things like that, but he'll join us if possible. I'm Daniel Rico, PhD student, part of WINDMAP here for a few years. I'll start with the team has changed a bit. AJ Shankar is a postdoctoral student at the University of Cambridge now, and Ashraful Islam is in industry. A few states over now. So I, at the moment, am the last remaining member of the UNL student side of the project. I also would like to say I enjoyed the Weather Technology Forum, so thank you for hosting that in Tulsa. That was quite enjoyable. So my prior work was with the Tethered Aircraft Unmanned System, or the TOS, just kind of a diagram on the right there of what the nature of the system was prior, which is just some sensors embedded along a power tether to a quadcopter. Our current work is wanting to derive wind speed from the localization of the tether in space throughout the duration of some type of flight or trajectory. And there's we show here that if we have an accelerometer and gyroscopes on board, we have the hopes of being able to derive perturbations to the expected catenary behavior of this suspended line between the UAS and the fixed ground station, which is expressed as a hyperbolic cosine function. So our initial thoughts are any deviations to the expected behavior of this localization based on general physical phenomena in the environment, we would attribute to perturbations due to wind at that portion of the lower atmospheric column. The reason that's interesting, one is for WINDMAP, and also we have another project that has to do with the agricultural side of the application, specifically with evapotranspiration. And the Penman-Monteith equation is parameterized with respect to things such as wind at altitude. So we were hoping to be able to do both of these things at the same time. In order to do that, we are doing some lab experiments. I am for this project in the winter here that just passed and continuing forward here into the spring. We put together a small circuit board with a microprocessor in a wireless transceiver and a commercial accelerometer and gyroscope, similar to that which you would find inside of a flight management system or flight management unit on a quadcopter. In order to test this system, we embedded them on a physical tether, a non-power one, just a physical one, in the laboratory setting with motion capture markers on each of these little printed or these little perf board circuits in order to create objects within a Vicon motion capture environment. So then we can get a ground truth for their actual positions in space. And could you move to the next slide, Dr. Jacob? Thank you. Here's just a kind of like a still frame of kind of a situation such as this, where we have that physical tether with these little perf board circuits that are objects in a Vicon environment suspended in the presence of a variable speed fan. That just is an exaggeration of the type of wind that it may experience at various positions along a column, so we can adjust the height of the fan and its angle and so on and so forth and speed, and have an anemometer present so then we can know at different distances in the cage what the expected behavior and speed and force and direction of the wind would be. And then we're hoping to be able to, as we speak, we're running experiments and pulling the information from the Vicon system and from the onboard accelerometers and gyroscopes in time at as high frequency as we can from these systems. And then attempting right now to calibrate and filter the system such that we can see and derive these perturbations. I think, in a nutshell, I think that's what recently we've been working on the side of observations. And as I said, I work with Dr. Carrick Detweiler. And that's all I have, Dr. Jacob.
Huh. All right, thanks. Sorry, I lost my controls there for a second. So thank you, Daniel. I appreciate that. Do we have any questions for Daniel? I'd like to get it started off. And Daniel, we are doing some other similar tethered applications. I'd like to do some comparison. So let's talk offline. But our sensors are quite a bit different from what you're using. So I think it would be a good comparison between the two sets.
Yeah, absolutely. That sounds like an interesting comparison we could do.
Okay, no further questions or comments. We'll move on to Virginia Tech with the McConan. I know Craig couldn't be on this morning. He has a PhD exam, but McConan is filling in for him. So Conan, go ahead and let you get started.
Thank you. Good morning, everyone. So just a couple of brief updates regarding what we've been working here at Virginia Tech. And so essentially our ongoing efforts are still the wind estimation from unsteady aerodynamic fixed rate motion. And so, but before I say that, I guess I could say that the two major objectives that we have in our lab here is to, number one, develop the direct capability to measure wind, both from a fixed wing and a multi-copter. And that would be mainly used to reconstruct gusts so that we can validate some of our estimation schemes. And then once we have that, essentially what we like to do is, and we've been working towards, is to develop both for fixed wing and a multi-copter aerodynamic models to do model-based wind estimation. So our efforts so far are going in that direction. In terms of some of the papers that we've submitted, will be at SciTech. I think, well, I'll be there. Chris will be there from our lab. Jeremy will be there, Dr. Woolsey would be there, and we've submitted at least one paper to my knowledge so far, titled Wind Estimation Using a Fixed Wing Model Based from an H infinity filter by Chris and Jeremy and Dr. Woolsey. We've also submitted a modeling and identification of unsteady aerodynamic modeling for a small fixed wing to Journal of Aircraft. So hopefully that gets accepted, and you'll see it soon. And so we have two platforms, and they've been both instrumented with direct wind measurement capability. The fixed wing that you see here is what we call the MTD, and the other one is the hexacopter, and that we're still working on instrumenting it with a sonic anemometer for validation. And what I'm showing in terms of plots below is essentially using the fixed wing, and we flew this aircraft for quite some time in a grid pattern, if you can imagine that. At some constant altitude, and we for that day we had an expected forecast, and we wanted to see if we could validate our ADU or our direct measurement with that. And the result was the mean velocity that we reconstructed matched the forecast the expected values that came from the forecast. And so that's from what you could see. Essentially, the plots that I have that we're showing here. From the 3D gust reconstruction is the direct gust reconstruction from ADU measurements. Next to it is just the same data, just represented in a different format or from a different view. It's a 2D gust reconstruction. The yellow line is essentially the direction in which the aircraft is flying and the speed at which it's flying. So the radius from the center shows the velocity of the aircraft in meters per second, and then in degrees in terms of heading. What you see here in blue are essentially the point measurements, or essentially the measurement, the direct measurement of wind at a given time from 0 to 400 seconds. And if you can see it in the middle, there's a red line, a red dot, and that's the mean over, I think, an 8-minute period. And so that's just to say that our capabilities have been validated by some of our forecasts. Going forward, what we would like to do is both from our model-based estimation, from the aerodynamic models that we've developed, to essentially be able to predict this without using the ADU. So that's it. Any questions?
Yeah, great. Thank you. Nice work, McConan. And so just as a comment, we've had both the Virginia Tech and University of Kentucky teams do a couple of collaborative flight demonstrations. First at the Bluegrass Station, where the Virginia Tech team and myself met there previously, and then we followed up with a visit to the Virginia Tech site. And I do know that there's some collaborative work with NASA using some of the LiDARs at the Virginia Tech site as well. And so I don't know if anything that you want to add on that or not, but McConan or Grady.
From my part, not so much, but thank you for mentioning. I forgot to mention it, but yeah, we've done some collaboration work both with the UK team and also NASA. So I don't have an update regarding that just yet, at least.
Great, thank you. Any questions from McConan? All right. With that will close out most of our observational reporting. This is really only scratching the surface in terms of what the team's been working on. But obviously what we're doing is highlighting the current efforts. So if you have any interest, for those of our guests on the call today, please let me know, and I can certainly point you to some of the more details, including some of the publications that are listed in the references portion of the presentation. So with that, we'll move on to our next group of presentations, and we'll start off with Adam. Adam, it's all yours.
Thanks, Jamie. So I'm going to start talking about this work that was led by one of my undergrad students, Ryan Martz. But before I jump into it, I kind of want to give a brief overview of the work that my group is doing that's relevant to the WINDMAP effort. Several of them are funded directly, but some of them are not. But I figure, while I don't talk about it specifically in this presentation, I want to give a nod to it. So obviously, first I'll talk about the urban heat island, which really is more than an observations, kind of fits in the observations category. But we also have work that Stephen Shield will present later on machine learning predictions of thunderstorm initiation. As Sean mentioned, we are continuing to work on this rotor wash analysis and hope to get more data this spring or later this winter. Still working on the logistics of that. And finally, though not funded by the NASA effort, I do have a student, a PhD student, Matt Wilson, who some of you know, who's doing the assimilation of observations into numeric weather prediction models in a data denial or OSI framework. Again, I won't talk about it today, but if you're interested in that, I'm happy to chat offline about it. Okay, so next slide. So this is something that this is Ryan's presentation from the annual meeting, which I won't go through the entire thing. I'm going to go quickly through it in the interest of time, but briefly, urban heat islands have been something that we've known about for many, many years. And a bit more recently, there's been a increased interest in understanding the impact of urban heat islands on precipitation. And so we wanted to jump off that prior work and ask the question, are urban heat islands affecting the initiation of thunderstorms, what we call convection initiation or deep convection initiation? Next slide. There's a dynamic reasoning for this, why they might affect thunderstorm initiation. It will affect the thermodynamics. So obviously you're going to get heating associated with the urban heat island, change in the moisture content associated with the urban heat island, but also that change in the thermodynamics could impact could create air mass boundaries that could aid in initiation. Hey, Jamie, can you jump to the next? There we go. So briefly, this work is essentially to understand whether urban heat islands do impact the frequency of convection and to what extent what kinds of conditions environmentally, as well as the intensity of the urban heat island might affect convection. Next slide. So we're using a data set that was developed by Stephen Shield that it's based off the Thor algorithm, thunderstorm observation by radar, we've used for prior work. What Stephen has done is extend the data set for across 11 years. Stephen will be talking about his work later on. This is the domain covered by the data set. As Ryan notes, in this specific project, he's using 30,000 thunderstorm initiation points. The total data set includes well over 1 million initiation points, usually about 200,000 or so per year. But so Ryan's just using 30,000, and the reason is because, and you can go to the next slide, he's only looking at specific cities within this region. Now, this is the basic distribution of thunderstorms. I won't talk too much about this, but in general, this is the domain that's covered, and of course, you see hot spots and initiation on the mountains and near the Gulf Coast. Next slide. So the cities that Ryan considered are all what we call medium-sized, 200,000 or more in population. We did break it into different categories of population size, but all of them are over 200,000. And you can see the cities that we used. Next slide. We broke it into small and large cities, ones that are more than 1 million were considered large. We also separated the Gulf Coast cities, and I won't say much more about that, except that in general, most of the observation, most of the analysis that we conducted excluded the Gulf Coast cities because of the impact of the sea breeze. Next slide. We did use the RAP data. So this is model analysis data to quantify the strength of the urban heat island. But maybe more importantly, what we wanted to do is create a data set that was in a rotated frame of reference. So it's a natural coordinates where the urban heat island is situated the same across all cities and all conditions. And so essentially what you'll see in some of these next results is that the coordinate system is rotated so that the urban heat island, or the urban area is in the middle and the wind is blowing from left to right. So all the data have been partitioned in that way. And he looked at seasonal impact, diurnal impact, as well as the strength of the urban heat island. Next slide.
Check, 1, 2. Check, 1, 2.
Yep, it works. Imran. And so this,
Sorry.
no worries. This is the rotated frame of reference based on the boundary layer wind. So all the initiation points are organized relative to the urban area in this rotated frame of reference. Next slide. There are a couple of important definitions here. So we broke it into downwind versus upwind, but also the term downstream will be directly downwind. So where the urban area is in the middle at A, the downstream is in that sort of polygon FBCG, and that is directly downstream, and the size of that polygon is a function of the size of the city. So downstream represents directly downwind of the city, whereas downwind just means generally to the quote unquote east in the rotated frame of reference. Next slide. With the last thing I think it's the last thing I'll talk about in terms of the method, we calculated this perturbation, which is the density of the CI points downstream relative to the density downwind. And so the analysis that I'll present here, and there's more analysis that Ryan did, but I won't talk about, focuses on the perturbation of the downstream density relative to the downwind density. So the idea here is if there is a higher, what we call P density, then it means that there are more CI points downstream relative to downwind. Okay, next. And you can hit if you hit this slide again, it may advance to highlight. Yeah, yeah. So in general, the P values here are how we categorized. Obviously, low P value 0.01 means that it's statistically significant at the 99% level. In general, what we find is that overall, there's a statistically significant at the 95% level for all non-Gulf Coast states. That is, that there is a higher percentage downstream relative to downwind. In the fall for light and medium wind to some extent, and importantly for weak urban heat islands and not strong urban heat islands, we see a statistically significant higher density in the downstream versus downwind. But it was kind of interesting that we saw this for the weak and not the strong. We're still investigating why that might be. Fall as opposed to summer and spring, to some extent, maybe not surprising. Light wind and medium versus strong, again, that is not terribly surprising because we would expect strong wind perhaps to have larger mixing and in some ways mix out the effect of the urban heat island. And at night, you'll notice the p-value is pretty low. In other words, that at night, the signal is also most prominent compared to during the day. Next. And these are box and whisker plots, and they say basically the same thing, and I won't dwell too much on this in the interest of time, but essentially, while there's a lot of spread, and certainly for some of the distributions, and this is broken down at all those individual categories, for almost all of them, we see that there is a positive value of P. In other words, the downstream density is higher than the downwind density. Next. I think the next slide is highlight. This is an actual illustration of the density to kind of sanity check the results. Statistics don't say everything, obviously, but this is just for night. But you see that the concentration downstream is indeed higher than downwind. And this is for all of the cities. Okay, next. So very briefly, the takeaways, there certainly seems to be more convection initiation downstream relative to downwind. We also looked at upstream, downstream versus upstream. A similar result was seen. We ignored the coastal areas in part because, no, not in part, mainly because of the influence of the sea breeze. But there's some interesting results there that we might dig into a bit later. And the urban heat island magnitude is something we need to explore a bit more as well. I think that may be it.
Yeah, that's the last one.
Okay. All right. So
yeah, my bad. You're lumping you into prediction. I should have said this is. I consider this more transitional since it directly feeds into. We'll be going on the prediction side, but obviously we're on a spectrum here. So
yeah, sure.
So with that, Adam, I would ask, right? What are the next steps in terms of how to utilize this?
Well, so I can tell you what we're going to do, but I mean, I think more broadly, I know that this project does have a focus on the urban canopy, and so I think it's worth either directly focusing or using this project as an opportunity to focus on why it is that the urban heat island signal and CI exists. And we can hypothesize the impact, of course, on the thermodynamics, but are we seeing structures kinematically that might result in enhanced initiation downstream? That might be something that comes out of some of the field work or large eddy simulations that I know James and his group have been doing. So I think it's something that we should be maybe capitalizing on based on this project if we don't necessarily directly focus on it with the project.
Yeah, it seems like there's a lot of advantage to using this as a jumping off point. In addition, just to better understanding what's going on in terms of the physics.
Yeah.
Do we have any other questions for Adam?
Adam,
Hey, Adam.
thanks for this. It's really exciting. I'm especially interested in, you had slide 41 where you've sort of put this, and I assume this is from all of the cities sort of put together, convection initiation per square kilometer.
Right.
Can you say anything about the typical range of variation? And your perturbation analysis started to get on this, but maybe which ones are significant, and also like there's something in kind of the southeast almost corner on this, right? That that localized red hotspot. Does that have any significance because it's from multiple data?
Yeah. So the variance is something that obviously we were very mindful of, and something that isn't necessarily captured in the statistical analysis, but might be when you do analyses like this. It's something we need to explore further, for sure. And I think we need to look at all of the distributions, all the subcategories in this context as well, partly a sanity check again, but also as indication of variance. In terms of that hotspot in the Southwest, I don't know. I mean, it clearly is something that has shown up in this overall distribution, but I don't know if this is because there was one city that happened to really highlight this, and that this is effectively not a meaningful pattern. There, one aspect of the study that I didn't present is a hotspot analysis, where we actually didn't visualize it like this, but actually quantified hotspots of CI and then partitioned it in kind of in this frame of reference, and it shows something different. And so I'm not going to speak to it, but that's another way of looking at these data that I think is maybe interesting. And also the other thing is, I didn't talk about individual cities. I mean, it's likely that there will be cities that have, well, we know that there are cities that have a signal, in other words, that don't. Overall, clearly there seems to be a pattern, but it's very likely that some cities show this much more prominently than others. And that's another part of the analysis that we intend to pursue.
Hey, thanks, Imran. I think I heard James with a question.
Yeah. Hey, Adam. I may have missed it, but did you look at the upstream stability as well, and how that played into the frequency of downstream initiation?
No, we didn't. No, we didn't.
Okay, I'm curious about that
Yeah.
because it's probably going to be, well, I'm sure there's got to be some kind of relationship. How many cities went into this analysis?
18? Can't remember off the top of my head now. Yeah, it'll be here somewhere.
Well, here you go.
Yeah. Count quickly.
Cool.
It's like 15, I think, in the non-Gulf Coast, something along those
Yeah,
lines.
looks like these are the same lists.
Cool. So basically, it's sort of the center of the country.
Right.
All right, thanks, Adam. Really exciting
Yeah.
stuff.
Yeah, thank you.
Thanks, guys.
All right, with that, we'll move on to Imran. We know
Adam,
your mic
thanks.
works now.
Adam, thanks for that. Somehow I have two mics. They're supposed to be in series. Turns out they're in parallel. Let's see. We're getting into some structure identification work. Really embracing the WINDMAP title here. It's saying, let's start to map some of these wind contours. We started with some kind of localized vortices, tornado structures. Obviously, we're more interested in the urban world, but so for proving out some of these concepts and some of the operational side, this was an area where we could really start to bring down the uncertainty because we have some stable structures. And so we do have some plans to look at basically more involved structures and actually some experimental work that can really only be done in the summer. And so we're basically gearing up for summer at this point. We got some groundwork and some early measurements in place last summer and are excited for this summer. But I mean, so this will give you sort of the cartoon version of the problem. If we think about a localized vortex or a tornado, and in 2019, a couple of tornado models started to become available that had sort of this reduced order framework that would be appropriate for this kind of thing. We've got basically 4 different parameters that we could parameterize that with. We could generate a flow field, and then we could start to look at how UAVs operating in that environment can recover information. So we're using wind inference algorithms rather than direct measurement, kind of like what McConan talked about there. And so we're looking at, can we start to use the existing population of UAVs to infer wind maps? So this kind of gives you an idea of the setup. Effectively, we're looking at things like, can we minimize error average across multiple UAVs in terms of the estimated quantities? And so we've set up the identification process with this sort of structure. It ends up being an argmin process over the parameters. Next slide, please. So this can kind of give you a little bit more on that minimization approach and how we could do that dynamically. On this next slide, the idea is that now we have vehicles flying in real time. It hasn't updated on my side. That might have a delay. Okay, there we go. So vehicles are flying in real time, and they have control over their trajectory. They in a disaster recovery scenario, they may not even have connectivity with a ground station, but they're able to basically fly into positions where they can manipulate their trajectory. And there are regions of the flow, depending on what you're measuring, that are more informative than other areas. And the way we quantify that is within an information term. And so we can look at information term. Basically, the biggest term in the information has to do with the spatial gradients. So they're looking for gradients in some sense. There are some other terms that you need to add in there to make it work well. And that's the focus of one of our SciTech papers, is what do you actually need to add in there? We make it into a constrained minimization when we have an actual vehicle, because the dynamics start to constrain that vehicle. And so then it becomes a constrained minimization problem. But each of these vehicles can solve this locally. And so, we pose this. There's 2 examples here. If you go to the next slide, you'll see kind of an example of what this looks like for a simple, just a simple rotation. It's the AZZ Ash Zucker Warren Zardeman 2019 vortex model. And basically on the left, you see, what the flow field looks like. In the middle, you see basically the relative information level of a particular trajectory that is associated with this vehicle just trying to find the max spatial derivative, and it does have a distance constraint in there that has to do with the flight speed. So in other words, as it drops the next waypoint, it has to drop that at a very specific distance. So effectively, what's happening, you can inside the tool here is you can see inside the optimization, which is going real time individually on the individual vehicle, it's looking for where the entropy is, which is a sort of the inverse information, and it's looking for the minimum point there. So if we unwrap that, if we're choosing if we're at a constant speed, like a fixed wing aircraft would fly at, we're basically looking for a direction. And so we can unwrap the compass angle here and look for the minimum entropy and choose that. And when we do that, we get less than 10% parameter estimate error. And the most information has to do with the relative radius. So we've got some other example, I think 5 or 6 examples that we'll walk through in the SciTech presentation. But if you go to the next slide, we want to talk about, this is just for a single vehicle. If we start to look at multiple vehicles, now we need a way to fuse that information. And we need a way to fuse that information in a way that respects the network congestion and basically shares the least amount of information. So some of our underlying estimation algorithms looked at multiple vehicle estimation earlier on this project, multi-sensor estimation, and now we're starting to think of these vehicles as sensors and how do they fit into that. So one way to do that is what we call a federated Kalman filter, and so we used kind of that template to look at how we might fuse wind estimates for multiple vehicles that are each pursuing their own contours. And one of the surprising things that we found was that the information federated structure, when you put all of this federated fusion, which is defensible, with lots of, with theoretical derivations, it actually underperforms the most accurate agent. And so we thought, we started thinking about why that is and investigate a little bit farther. If you go to the next slide, we can see an example of where that is and really why that is the case. So if we're looking at the distance from the center of the tornado in the top left, basically we have a weight function that has to do with how that information is weighted. So in other words, what's going to end up happening out of this term is that the highest weighted information is going to be the vehicle that basically flew closest to, in this case, the core radius, and was able to identify that core radius, really transitioned it. So it can't actually just fly on the contour because you actually get no information. You get no gradient, no difference there. You really just got confirmation of your current view. And so then there's a different weight function for the core radius and for the positions. And so if we think about, where the most information is, that's where it is. And so the vehicles that are, in those locations are the ones that are going to be weighted the highest. But the issue is here, in the multi-agent case, if we're doing some kind of a weighted average, which is what a federated Kalman filter does, it just has weighted terms that have to do with the covariance and the uncertainty. Then effectively a weighted average can never overcome a bias. And so that's kind of what's pictured in this bottom left, is that we have two agents here, A and B, and those agents are in the same quadrant. And so they're going to have a bias in terms of the core radius that they estimate relative to something that would be able to basically circle the vehicle. So I think you can click, and there's just an animation that sort of shows, when we fuse those estimates there, we get basically the red line. The true is actually a different value. And so this is what's going on here. So designing biased estimators or estimators that work in the presence of bias is actually a narrower field than sort of it's not the thing that you typically do, right? Typically we can remove the bias or we can estimate the bias. And so ways to smoothly incorporate that is our current work. I think that's everything I have today.
Thanks, Imran. Great stuff. Do we have any questions for Imran?
Imran, this is Apurva from Climavision.
Sure.
We'll get into this a little bit later, but we're starting to pick up tornadoes now with this network of radars that we're deploying, especially getting very low altitude views of tornadoes. We picked up some in Georgia recently. Maybe we take this offline, but is there interest in data that we are gathering? It seems like you would be interested really in the data that matches with the flights that you took, so they would have to be at the same location. But can you talk about that a little bit?
So we're really excited for your sensor rollout. I'm excited to. I think you have an update later that we'll get to hear about how that's going. The typical sort of update rate on the existing radar hasn't really supported this kind of dynamic replanning. But I think we can integrate it as a sensor with a different timescale, or if you're pushing the limits of the radar update rate, that would be another way to say maybe we could somehow dynamically update this kind of thing. Because one of the things that we do is when we first go out, we have sort of a stereotypical idea of where a flow feature might be. And so that's what we start with. And then with every successive data point, the picture builds up. And so we do need some initial kind of guess in order to do this kind of work. So yes, I'd be interested. I look forward to your talk.
Great.
Thanks, Apoorva.
Imran, there's some pretty high resolution, large eddy simulations of tornadoes, and not just the tornado itself, but also the parent supercell, that maybe you could use those as a way of either conducting, I won't say an OSSI because I'm not sure that's appropriate for what you're doing, but at least have a model field at very high resolution, very high updates that you could use to test this. And I mean, it's a follow-up part of that comment is that I wonder how your model performs when there's, I won't say noise, but turbulence or uncertainty. I'm going to say uncertainty, but just variability in the inflow or around the tornado. Does that disrupt the ability to converge on an accurate representation of the tornado?
Right. So I think there's two things, right? We definitely have to solve the turbulence problem, especially if we're going to operate in the urban areas where we have, I mean, there's not a current sort of, here's the stereotypical shapes that you'll see, and the ones that we do see are unsteady, right? So that's the context that we're putting this in. And yes, we do have to incorporate turbulence. The nice thing is that often turbulence is zero, doesn't have this bias, and so in other words, it's increasing the uncertainty, but it's not necessarily moving that point. So yes, we haven't done that study, but we definitely need to resolve that. To your point about the CFD simulation of the convective supercell, we're excited about the work that has gone on there. We did write a couple of projects with a collaborator that had some tools there. In that case, the data set was large enough that I think she was looking at basically funding even just to sort of reformat it so she could send us that so that we could integrate it. And so I think just I think it was going to be a month to basically pull the data, the gigabytes of data set out. So we didn't ultimately get funded on that, but I think that's something we need to do in our future is, test this against a really high fidelity case. And Sean got us, some measurements in terms of an experimental world, which is great, except we don't know the truth, right? And in that case, there wasn't a well-defined feature there. So we're, yes, we can come up with estimates of what we think the features are, but we don't know the truth. And that's where you need the really high fidelity numerical tools. Thanks for all the questions. This is great.
Anything else for Imran? All right, good discussion. Okay, so back to UNL. Stephen. Yeah, this is getting now into a bit more what I consider transitioning to the prediction side of the project.
Yeah, so if you want to go to the first slide here. Yeah, so just kind of tying this back in with the WINDMAP goal. My project is trying to predict a microscale phenomena, in this case, thunderstorm or deep convective initiation, with mesoscale model input, in this case, from the rapid refresh numerical weather prediction model. And to do this, I've kind of used the random forest machine learning model with 12 different RAP-derived environmental variables. And I've kind of looked at the overall feasibility or skill, as well as maybe the best approach for doing this. So to do that, I've kind of focused on spatial aspects. So kind of as a background, other previous studies have attempted to do similar things, but they've typically been focused on data from a fairly small area. So in my research, I've developed models both for our full study area, shown in the central US here in the red on this slide, as well as for kind of smaller regions, and looked at how model skill varies when you're developing a large model over a large area versus a small regional model. And just kind of basic summary, we found no matter which region, the full model or the larger data set model has better skill. And if you want to go to the next slide, now we're kind of digging deeper into this. So how does model performance vary across regions? So if we look at performance in those kind of 4 subregions, how much does the predictability of DCI change across those regions according to our models? How well do these regional models perform in the region they were developed versus other regions? And then finally down here at the bottom, how do the different environmental variables that we're using in these models to make our prediction, how does the importance change whether we're looking at the full region model or the different subregions? So for example, here, if we look at Cape, the model that's developed in the Southeast has a much higher weight on Cape than the other models. So that's kind of what I'm working on now, is analyzing some of that with really the goal of kind of informing it and determining how best to proceed with some sort of operational or algorithm that's predicting DCI using machine learning.
Very good. Thanks, Stephen. Do we have any questions for Stephen? Just tangentially related to this, there was a National Academies report that was recently released on the use of AI machine learning on environmental sciences, and weather was a big focus of that. If you haven't read that, that's a good thing to look at from a kind of a broader perspective and where things are going.
Yeah, I haven't had a chance to read that, so I'll have to check it out.
All right. Thank you again, Stephen. Next up, we have Keith. Are you online?
Yep.
All right, Keith, it's all yours.
Right. Whoa, what happened to my camera there? All right. So, yeah, a couple things we're working on here. We had done an OC study on a spring case that is kind of finishing up here and getting ready for publication. Won't dwell on that too much. Winter case. So we wanted to see that case focused on CI, and then we also had some interest to see. One of our motivations was kind of thinking along the lines of like the 3D mesonet, and so for those not familiar, OC means observation system simulation experiment. So we're simulating the 3D mesonet kind of in this project. And so the winter, we wanted to, that was spring for CI, and then for winter, of course, mixed precip. So maybe the 3D Mesonet could help us diagnose areas of freezing rain versus snow, etc. So we have this case been looked at it before from 19 February, and one of the first things in the OC is to generate a so-called nature run that you treat as a truth. So the key thing with that is to make it as accurate as possible. So we had tried a little bit of that earlier this year, or in 2022, and I wasn't completely happy with the results. So next slide. So the result was a little bit on the dry side. We seem to have some kind of bias there. So we running these on our Oscar Sooner, which unfortunately had a lot of problems for the first time. We've been using this Oscar for a long time, and they had a lot of issues this year, but we did finally get all these through. So we're doing different permutations of these three main parameterization areas in the numerical model that we're using for the so-called truth. So these are the ones that we're testing, the different microphysics and the planetary boundary layer and land surface scheme. Next. So this is kind of the initial setup using the NOAA MP. We found that this is where the RH bias, the humidity bias, comparing against the actual Mesonet OBS. Next, go through these real quickly. Anyway, so the second panel there, you see the when you change to the ruck, pay attention to the scale, it changes. So the RH bias, there's a little bit of a positive bias actually in the beginning, but in the afternoon after 18Z, very small bias when you change to the ruck. So we figured that was the best way to go. And then versus the MYJ, MYNN, the MYNN looked to be a little bit better. It started off with that higher RH bias, but it like the mean absolute error in the mid-morning was a little better. Next. So then we kind of had to decide, okay, we've got ruck and MYNN, and try different of the microphysics, because the microphysics among the others didn't seem to matter too much compared to varying the PBL scheme of the surface. So using this, you could see the green line, which is the Thompson, seems to have one of the better performances and is accepted as one of the better performing in general microphysics methods. You could argue for Morrison, it's roughly the same. There's pluses and minuses if you compare them, but they're roughly the same. And Morrison, it seems to me, based on some other projects I'm involved in, is kind of being not quite as heavily favored in the literature and other uses. So I'm probably going to go ahead and focus on Thompson. Go to the next slide just real quick. This is just showing on the left one of the poor performers and how this shows up. So we've got this weather moving in from Texas, coming up from the south there. This is 19Z, which is 1 p.m. local time. And the dark dots there are the actual Mesonet OBS, and they're colored in the same manner as the forecast field, so they should match. And you see here the darker colors, mostly in western Oklahoma there, and a little bit in central and northern, and it's higher RH in the forecast field that matches better on the right-hand side. This is just the map view of the statistics that I was just showing before. Next is just the temperature, same thing. On the next slide, there we go. So yeah, these also match. You don't see as much variation there from one to the other, but in west central Oklahoma, especially there's some of those blue dots there that are in the lighter yellow. So they're too warm, which kind of, it's all tied together between having less humidity, probably more surface radiation reaching the ground. So that's where we're at. I feel like we settled on a good combination now, and it should go pretty quickly to try to generate I have to modify my code a little bit to do this case versus the original one, and then we can start running the different experiments within the OC testing, the simulated 3D mesonet, the simulated surface obs and so forth, and look at various combinations of those and see how that will impact the forecast. And then for those that are not familiar, we then verify against this nature, which is, we treat as the truth at this point. So we'll have everything, even though it's not always observed, like the actual forecast profiles we'll treat as the truth, and compare our forecast using those various data sets to the output from this model. And in this particular case, we actually do have some UAS data too, so we can compare that. I haven't done that yet. I should probably pull some soundings out of that final truth data set to compare to the actual OBS that we have for this set down in Washington, Oklahoma, south of Norman. We have some OBS.
Yeah, that sounds like the natural next step on this, Keith.
Yeah, I probably should do that real quick and make sure. And maybe if the Morrison does better in that comparison, I might just go ahead and use that one. But they're pretty close. So that's all I have.
Thank you, Keith. Do we have any questions?
Just Keith, yeah, I had a quick question.
Yeah.
So I was curious about the relative humidity evolution throughout the day. Is it consistently more moist using the RUC land surface model, or is it more during the daytime hours that you see this bias improvement?
Well, it's mostly in the afternoon where it was too dry. I think it's all interrelated with maybe there's more sunlight getting in. Of course, it's sensitive to the surface, land surface, so it might have to do with moisture flux from the surface. In another project, we were looking at some winter flux issues, actually in the FV3 model, but it was surprisingly sensitive to things like snow cover affecting this flux of moisture in different models. It was kind of interesting that you have to get down deep in the weeds to see which term is affecting these local moisture changes. So, but yeah, it's mostly in the afternoon. I don't know if Jamie wants to go all the way back to the beginning, but in that second slide, next one, no, too far back. Yeah, this one. Yeah, so you see the RH bias starts at 14 UTC. It kind of peaks in the mid-afternoon, 1920, and then as it gets toward the early evening, the RH bias is still a little bit dry, but it's only 5% or so, which is pretty good.
That's interesting. Yeah, I agree that it'd be interesting to see how it evolves throughout the boundary layer too. So if you do have the UAS observations to compare with, that would be useful to look at.
Right. Yeah. I'll have to look at those more carefully.
Keith, are these the free forecasts, or are you simulating and then showing the analyses?
We're just doing the nature run here, so there's no data. So we're just trying to create the most accurate. In this case, we're using a nested WRF model at 1 kilometer interior resolution. And then we're going to compare that to another model run at 3 kilometers. So
right,
we don't have a hopefully with data, it could correct these things. But we're trying to create the best kind of artificial nature that we can, using the tools that we have. And obviously, if you're doing real forecasting, you can't be playing around with all these things, whatever. We know the truth, but we're just trying to create the truth here, recreate the truth, I guess is the best.
Sure,
way to
sure.
put
Yeah.
it.
I know that there is an approach developing in HRN where you simulate the data. And so essentially it is not just a free forecast. It's actually including the assimilation, not of the supplemental data, but of the data that are available.
I see. Yeah, well then, you kind of, you get into an incestuous thing where you want to create the data. Yeah, I can see that. You could create the nature based on a series of analyses even. But you're when we're trying to get down to 1 kilometer, we don't have that luxury. But yeah.
Okay.
Keith, real quick, Gus here. In February, Les and I might be near the Washington Tower collecting some more data, particularly targeting the winter weather observation, the freezing rain, and scenarios you were interested in. So I'll send that data your way.
Okay, yeah, contact me by email, whatever. I'll look at it.
All right.
Thanks.
All right. Thank you, Keith. And moving on to James. You had to get fancy with your title slide.
I had to close the blinds. It was driving me nuts. Thanks, Jamie, and thanks everyone that went before me. I think this feeds nicely into the overview that I'm going to present today on NCAR's efforts over the past year. You can go ahead to the next slide. So I'd like to start off with this. I mean, this is our big problem that we're trying to solve here, right? It's trying to provide weather guidance and analysis information at ultrafine scales that are required to support urban air mobility or advanced air mobility, particularly in urban areas. And the depiction on the right shows sort of the holy grail or the end goal of what we're trying to do here, and that is allow the user or the operators who are trying to do package delivery or ultimately people moving across urban areas to enter in what their planned operation routes are for the day. And in this example, I've got an inbound and an outbound flight that are color coded, with the orange being the outbound and then the return flight later in the afternoon. This could be a package delivery or it could be, people moving or transport across an urban area. And what the operators would like to know is, what is the probability of me completing this successful mission here, especially for package delivery, say. And so they would want to look at the wind field through an urban landscape, and particularly be interested in the headwinds and tailwinds along their flight route. And then if they're moving people, they probably also want to know something about the turbulence. How intense is it going to be along the route? Where do they expect to have potentially hazards that they want to avoid, or ground flight operations? And so obviously this information changes throughout the day based on weather conditions and their interplay with the urban landscape itself. And so I'm going to kind of give a high level overview of the different aspects of this problem and how NCAR is working to tackle this along with our collaborators at the universities across the country. Our next slide. So this is a team of researchers that we've assembled at NCAR with various areas of expertise and the different aspects of the problem that we're working. We have a UAS data assimilation component that's being, and you'll hear more about this from Junkung Kay after me, I believe. Kate Fassel has also been instrumental in developing the real-time data assimilation system using NCAR's Data Assimilation Research Testbed, or DART. We also have a team working on microscale predictions using GPU enabled large eddy simulation system called FastEddy that's been developed by Jeremy Sauer and Domingo Munoz Esparza. They gave some nice presentations actually last week at AMS. So if you're interested, I suggest looking those up that were partially funded by WINDMAP. And then I've been working with Ryan Sabash over in M-Cubed, their sister laboratory at NCAR, using machine learning to essentially downscale, mesoscale model information into local impacts that are aware of the building morphology of an urban landscape. Pedro Jimenez is also on the project, and he's sort of, one of his specialties is doing the mesoscale to microscale coupling and real-time simulations. And then myself as well, sort of providing overall guidance, project management, outreach, et cetera, field campaigns. So I'm going to touch on each of these topics briefly. So here is sort of the overarching goal again, laid out in terms of data flow. What we envision is being able to drive very fine scale simulations that you see on the right there. That's a depiction of the evolution of winds, low level winds in the San Luis Valley of Colorado. This was actually during a lapse rate field campaign that took place in 2018. And we were providing this type of guidance in real time. What you can see is an evolution of the wind flows coming out of the canyons during the early morning hours. These are drainage winds that are typically formed and driven by cold dense air descending from the canyons. And then you can see a transition as the flow. Here's the peak flow, and then it, I don't know what happened. It transitions to more of a noisy convective boundary layer in the early afternoon hours. But the key thing is that you really need to constrain these ultra fine resolution simulations with a really good mesoscale background, and that's where the data assimilation comes in. And so what's depicted on the lower left portion of this slide is the collection of observations with weather UAS or weather drones. These were collected during lapse rate. We had a suite of weather drones collecting observations throughout the northern sort of 2/3 of the valley. And so we can get these sort of high resolution time series, the bottom panel there, in this example, the winds again, showing how the winds are evolving with time and height. And so in this example, you can see that there's sort of some low level wind maxima that may be related to sort of turbulent eddies, pulling down some of the higher momentum air from aloft. And you can see sort of the fine details that you can get from weather sensing UAS. These data are then processed. Ultimately, they're probably thinned a bit because numerical models can't handle that level of detail. And then they're used to drive the initial condition, set up the initial conditions for short-term forecasts, which I'm showing here in the center panel. So you have an ensemble of simulations that you can create using the ensemble Kalman filter approach. You assimilate the observations into each of these members and constrain them to some extent so that they're aware of the current conditions. And then you pick a member. In our case, we would pick the sort of most representative member to drive the high resolution model that you see on the right. Next slide, please. So in terms of the data assimilation piece, we've been doing data denial experiments, otherwise known as observing system experiments. So this is different than what Keith was showing, where they're using synthetic data to assess the impact of an observational data set. Here we're using real data. And again, this was data that was collected during lapse rate. And I'm showing an example case study from the 15th of July, which was a convective initiation case. And so on the left, the control run is where we assimilate only the available surface observations in the valley. and the right panel labeled UASDA, where we're simulating both conventional observations and the UAS, a subset of the UAS data that was available during lapse rate. The scatter plots are showing the impact more closely. You can see in the color contouring that we're actually able to better capture the evolution of the cold pool. If you sort of compare the background field, which is the model analyses fields, to the up-down sort of upside down V profiles that were obtained with the independent UAS weather profiling UAS marked with that sort of magenta dot there. And then looking at these in more detail with scatter plots, you can see that we're much closer to the 1-to-1 line for, in this case, it's, I believe, potential temperature. We see similar type improvements in relative humidity and the winds. And so ultimately, with this improved environment, the right panels, you see the changes in the flow patterns. And one key aspect of this particular case was the assimilation of the weather observations from UAS much better captured the local convergence in the northern part of the valley. So you see the red purple couplet sort of in the northern part of the valley. That's indicating an area of enhanced convergence, and that only shows up in the UASDA simulation, primarily because of the observations that were collected at Moffett Elementary School, where we had profiling drones. On the lower panels, you can see that the difference between the control run and the run with UAS data included did a much better job of capturing the precipitation in the center of the valley on this day associated with convective initiation, so that you can see the comparison of reflective or precipitation accumulation in the colored filled contours with the stage 4 estimate of the rainfall in the valley. It does look like it's a bit more widespread than was observed, but there are some caveats there because this time there was no radar in the center of the valley. So we had a lot of underestimates. We believe that the precipitation coverage was underestimated at this time. Nonetheless, it does a nice job of capturing the initiation in this case. So this kind of reveals the importance of local UAS observations in predicting mesoscale phenomena. The next slide. So, and you can click on that, that's a movie. So once we have our better constrained mesoscale environment, we use this to drive microscale simulations. This is an example of a case, again, from Dallas, Fort Worth area, where we had a mesoscale or even larger, like a synoptic scale frontal boundary that passed through Dallas, Fort Worth. And you can really see the change in the character of the turbulence and the flow as the front passes through across the region, with strong northerly flow here at the end, setting up and inducing much larger scale turbulent features than earlier in the simulation that was prefrontal. So here again, one more time, you see the prefrontal flow is sort of from the southwest. And then as the front begins to come in here right now, you can see the flow shifting to northwesterly. You see the channeling through the buildings that are given by the gray areas. And then you can see the flow starting to speed up and the turbulent characteristics also changing quite a bit. If you click down, on the right, I think there's a climatology. So one of the things we've done is begin processing the data that was generated using these fast data simulations for an entire month. And you can create patterns of turbulence, sort of a climatology of turbulence that might be expected for an urban landscape using this technique. So this is just an example of showing where the turbulence is relative to the building locations, with the more purple colors indicating areas that are more prone to turbulence versus the yellows and oranges, which tend to be less turbulent. So this can be used for both, planning where you might want to have transport trajectories across an urban landscape, and also sort of timing of day. You can do this by time of day to understand when you could expect more intense versus less intense turbulence in an area. Next slide. So another thing that we've been doing, and I presented this at the AMS meeting, is to say we could use those simulations produced with FastEddy to relate predictor fields from a mesoscale model, such as the high resolution rapid refresh model, or the soon to take over for that Rufus model, to understand where turbulence might be expected using a machine learning technique to do the downscaling. And the benefit of this is that you can, once you train a machine learning model to do this, it can be run very quickly. So every time you get an update from the model, you can quickly run this machine learning downscaling technique to see where you might expect to see the strongest hazards. And so this is just an example of a machine learning algorithm that we set up to essentially train the model to try to predict those TKE values from FastEddy there in the upper left, based on a combination of the mesoscale inflow characteristics shown indicated by those profiles in the lower panel there, as well as information about the urban landscape and building morphology. So in this example, I have building tops, building density, and then a coupling of the information, such as the distance downwind from the nearest building or the upstream maximum building height, or a couple of the other predictor fields that we used. And then using random forest, 100 trees in this case, we can predict the probability of TKE exceeding certain thresholds that we might deem hazardous. And so in this example, we're looking at a threshold of 2 meters squared per second squared, showing the prediction that we get from the random forest technique, and then a comparison with the upscaled truth field. And you can see that there's a pretty good correspondence. So this is a sort of a quick and dirty research topic to see if it was feasible. And so now we're kind of starting to delve in and see what we can actually get, if we can actually improve this even further. Next slide. We've also been working on setting up a real-time capability for a couple of reasons. One is the planned upcoming WMO UAS demonstration campaign, which is planned for 2024. And another is to enable us to support this project so that if we have some planning, some planned field campaigns, we'd like to demonstrate sort of an end-to-end system where we could get the data from UAS in near real time and process it and get it into a numerical weather prediction model via, in this case, we're using, again, DART, but a real-time version of that. And what we'd like to do, again, is compare the skill of the predictions using the conventional observations only versus those that we can get with assimilating UAS observations. And so we're continuously collecting and archiving the conventional observations that we have. And we have other projects such as the one called WINDMAP, which is looking at trying to use UAS observations to improve the prediction of fog for an airport. And so we're sort of leveraging that project that's funded by the FAA with the work that we're doing here. So this system is currently set up and ready to go. And we think that we could probably use that possibly to support some field work here coming up that we will discuss at the end of this meeting. So we're excited about that. There's one more slide. Yep. So we've also been supporting UAS field experiment planning and participating, as I mentioned, lapse rate. We also have a site in Boulder we call the Marshall Field site, where we have the unguided tower that you can fly UAS next to do some calibration and validation type studies. And there's a number of others in this group who are either planning to or have used this tower or facility. I mentioned FogMap is another field experiment where we're assessing the value of UAS observations to predict and improve the predictions of fog at an airport. And the WMO UAS demonstration campaign, which is being planned for 2024, is an international effort to assess the potential role of UAS, particularly weather UAS in supporting operational meteorology. And So a lot of us on this project are also participating in or planning to participate in that upcoming field demonstration. So I think with that, I'll stop and take any questions.
Thank you, James. Nice work. So I do know Gus will be talking a little bit about what their plans are for the Marshall Field site near the end, but do we have any questions for James?
Hey, James, how do you guys do the, or rather, do you do an eddy seeding in fast eddy to get turbulence initiated right off of the domain boundary?
Yeah,
I was curious
exactly.
about that myself because you can see how that evolves from the spots.
Yeah, we do. There is still an edge probably that may have been cut off, but there's this technique called the cell perturbation technique that Domingo developed that has been published or has been actually we've gotten accolades for its sort of utility and simplicity. You can see sort of on the edges there is a little bit of a ramp up period, but we do some seeding at the boundaries, the inflow boundaries. And if you're interested in the paper, let me know. I could send that to you.
Yeah, actually, if you could do that, that'd be great. Thanks.
It's it should actually be available in the WRF LES distribution, the most recent one.
Yeah. Okay. If it's that, yeah, I'm familiar with that one. So, all
okay,
right, that was a different technique.
Okay. Yep. Good question.
Hey, James.
Yep.
Hey, it's Greatly. Can you go back to your integration and campaign slide? I think it was your last slide there. Yes. So I'll just say, you and I have talked about this before, and not specifically about your plans for 2023. So I'll just put a pin in that note that you and I should talk about these field tests, because we'd be very interested in figuring out if there's a way to be involved and contribute to this with our safety system.
Yeah, I think that's great for future planning. Particularly if we can get into an area where we're trying to do more beyond visual line of sight type operations.
Yeah. Okay. Yeah.
Yep. But yeah, that's it. We talked about talking and then we weren't able to do it. So
haven't done it yet, but we will. So
yeah, that sounds good. Thanks, Greatly.
Absolutely.
Okay, thanks, James. Lots of great stuff going on here. We aren't done with NCAR yet. So if we want to move on to Jung.
Oh, okay. Hi. Yeah, I'm Jung K, and I'm going to talk about the quantifying UAS observation error variance used in data simulation system and its impact on predictive skill. And this work is contributed by James Pinto, Kate Fossil, and Patrick McCarthy at NCAR. Okay. Oh yes. So in this talk, I have 3 scientific objectives here. So first, UAS has yet to be widely used in numerical weather prediction because this UAS is a very new type of observation. Therefore, we need to quantify UAS observation error using multiple data set to best use the UAS for data simulation. And we need to understand the observation error structure by UAS platform type and variable. And lastly, using this newly quantified UAS observation error, we try to assimilate the UAS observation and evaluate its impact on the predictive skill. Next slide, please. Okay, before I show the result, I want to explain the importance of observation error in data simulation. So in the middle panel, in the middle figure, DA is based on the Bayesian probability theory. So the figure in the middle shows that the PDF of observation in red line and model background in green line and analysis in blue line. Then the background is usually the forecast from the previous DA cycle, and analysis the initial condition for model forecast in the next cycle. And with this indicate their uncertainty, and we call them as the error variance. So given the model background and observation and their observation error variance and their error variance, we can determine the joint probability distribution of analysis shown in the blue line. So observation error is very important factor in DA for determining the weight of observation and background for estimating this PDF of analysis. So therefore, for more accurate analysis in DA, we need to quantify the realistic UAS observation error variance that represent the actual observation error structure in time and space. Next slide, please. So previous study from Jensen et al. Simulated UAS observation collected from the Lapse-Rate field campaign to improve forecast of cold air drainage case on July 19, 2018. And the right panel is the height time cross-section of observation and forecast. So the first one, the Doppler wind LiDAR, provide independent observation, and it shows the particle structure of cold air drainage and up canyon flow with wind direction shift. And the second one, the middle figure shows the simulation without data simulation, and the last figure shows the simulation after UASDA. And this result shows that simulating a UAS observation improved the timing of the change to up canyon flow and the magnitude of a simulated up canyon flow. And in the table shows the observation error used in Jensen et al. Study. Because this study was the first to explore the impact of UAS data from Lapse-Rate field campaign, the observation error were based on the commercial aircraft that is the constant with height. But however, the observation error should reflect the spatial variability of error in consideration of the characteristic of the observation. The next slide, please. Okay, so we tried to estimate the UAS observation error by referring to ANSYS and Ricky's study 2018. This equation, MS and COV are the mean square distance and covariance of the data. And this, in the original study, they quantified the radio occultation observation error using zone and model simulation. So in this study, we follow ANSYS and Ricky's approach using zoned observation collected from the Lapse-Rate field campaign, and also WRF simulation that is initialized by her analysis. And to apply this approach, we need to pre-process all data so that the UAS and WRF simulation need to be co-located at the zoned location. So we first collect UAS data within 20 kilometers from the zoned site and within plus minus 7 minutes from the zoned launching time, and sort the UAS data with the height with about 25 meter beam, and applied this ANSYS and Ricky's method to quantify observation error variance following this equation. Next slide, please. Yes. So this is the example of vertical profile of UAS zoned and WRF simulation on 18 July 2018, and here the mode indicate the different time when the zone was launched, and UAS data here black line, and zoned data in green line, red line, and WRF simulation in green line. And you can see that UAS and zoned shows very similar structure for temperature and Q. And the WRF wind simulation has a very large differences from UAS and zoned observation. Next slide, please. And this is the averaged UAS observation error variance vertical profile calculated using the previous equation. So black line shows the UAS observation error estimated by lapse rate field campaign data, and red one is zoned observation error. Zoned is the profile data that are used in the operational DA system, and the green line is the aircraft observation error variance that used in the Jensen et al. Study, and the red yellow one shows the sample size of UAS data. So in these figures, UAS sample size, sample number is mainly located below 400 meter height, and the temperature variance is very smaller than those of aircraft observation error variance and zoned observation error variance. And the UAS wind and RH error are very consistent with aircraft data, but are slightly larger near the surface and above 400 meter height. Next slide, please. So using this newly estimated UAS observation error variance, I conducted DA experiment using the same case and same model configuration with Jensen et al. Study, and I conducted two DA experiment. The first, the aircraft DA, I used the UAS observation error from the commercial aircraft observation error like Jensen et al. And the second DA experiment, UAS experiment, we used the new UAS observation error variance shown in the previous slide, and I used the WRF model and used the anchor dart ensemble DA system. Okay, next slide, please. And this is the DA result. I will show the ensemble mean analysis for Q and the mixing ratio, left panel, and temperature at the right panel. Two different observation error DA provide a slightly different horizontal distribution of analysis for both Q and T at 300 meter height. We sample the analysis and zone the profile at the orange dot point below 1 kilometer height and made a scatter plot as shown in the lower panel. So left figure is the scatter plot sampled from the aircraft DA analysis and zoned, and the middle one is the scatter plot of the UAS DA analysis and zoned, and the right figure is the scatter plot of the UAS and aircraft analysis. So aircraft and UAS DA analysis shows similar features except for samples below 300 meter in height in the yellow circle. So this means that assimilating UAS observation using new error variance correct the overestimate Q and underestimate T below 300 meter height. Next slide, please. And this is the same plot, but for the wind component, the left for the journal wind U, the left panel, the aircraft and UAS DA provide almost similar analysis, but the meridional wind V, the right panel, we can see that assimilating UAS data with new observation error variance shows more consistent analysis with zoned by correcting the first northward wind component below 400 meter height in the yellow circle. And next slide, please. And this is the forecast result. The two right panel shows the time height cross section, and height is the y-axis, and the forecast time is x-axis. And we verify the forecast using two independent profile, area, and Doppler wind lidar located at the blue and red dot circle in the left figure. And although the USDA analysis shows improvement just below 300 meter or 400 meter height. Their subsequent forecast provide different time evolution of Q and V wind. So overall, the temporal evolution of Q and V wind from USDA forecast are more consistent with profiling observation than aircraft DA forecast. So next slide, please. So in summary, the UAS observation error was calculated by applying the ANSYS method using the zone observation of simulation and UAS data collected during the lapse rate field campaign. And compared to the aircraft observation error variance that is used in the Jensen et al. Study, the newly estimated calculated UAS observation error variance is smaller in most height for temperature, while being similar for wind and RH. And the USDA with new observation error has impact on the wind and thermodynamic analysis at low level, better collecting large analysis errors than using the aircraft observation error variance. And the time evolution of Q and V forecast with new observation error shows a more similar pattern to observation than aircraft DA forecast. And however, in this work, we just used the limited number of sample that collected during the lapse rate field campaign. So we plan to use the additional data, for example, from the SGP field campaign and new observation, and also we can use the longer lead time of simulation. And if we increase the sample size, then we can get a more reliable observation error variance. And then also we plan to apply another method to quantify the observation error variance. For example, the Desarrollo's method that is very popular in DA community. So yeah, that is our future work. That's all. And please give me I'm happy to get any question.
Thank you very much. I appreciate it. It was impressive work. Do we have any questions?
Hey, I have a question regarding the Doppler wind lidar that you guys used. Do you by any chance know the make and model?
Yeah, it's what is it? The Wind Cube from the Eosphere. I don't know the exact make and model though.
Okay, thank you. That's fine.
So if I understand the process that you took, you made no distinction between types of aircraft, rotary wing versus fixed wing. Is that correct?
Yes, because I gave a talk about that result in the last meeting, WINDMAP meeting. So I skipped that one. But
Okay.
Yeah, I will. I will send it the result through the email next time.
Yeah, I'd be very curious to see that. Thank you.
Adam, so also we rolled up all the UAS weather observations because we just were trying to increase the sample size. But ultimately, we would like to distinguish between multi-rotor versus fixed wing. That we assume that they're going to have different air characteristics. Back to you, Jamie.
Yeah, sorry. I was just thinking about your comment there in terms of the air characteristics. I think that's an interesting question. I need to give that some thought.
Yeah, I mean, part of it is the representativeness error because if you're flying horizontal legs, you're going to be capturing some of the horizontal variability, whereas the multi-rotor is not really capturing that. And so that kind of leads back into some of the work that Sean's been doing too. And so we've been having a sidebar conversation about that a little bit.
I think we should open that up in terms of figuring out, making sure that we're capturing that, because I'm sure we have that in pretty much any data set that any of us take. But I'm not convinced of that either. So I think we need to have a further discussion on that.
Yeah, I mean, the profiling sort of in the center and then flying the fixed wings over some distance, longer is better, but whatever's possible, you know, currently we're constrained, I think, still with visual line of sight, but ideally we would make those even longer transects.
Yeah, move forward in discussions with the various test campaigns. Let's make sure that we're getting you the data that you need for that. Okay.
Yeah, and I think the tourist data would too also be very interesting to look at this coming spring. Do you have you have plans to have fixed profiling sites versus sort of long transect sites?
Yeah.
Yeah,
that's our ConOps is to have a near inflow, kind of like in 2019, near inflow mission that's just doing profiling. And they may move a bit, but it's a profiling mission, whereas the left flank would be horizontal transect. So we've had lots of conversations about calibration of these, and I think that's another aspect. One thing about the fixed wing is that you can do on-site calibration by doing orbits. I mean, as you do an orbit, you can essentially remove some of the theoretically some of the biases. But anyway, yeah, as the case with most of these items, I think this warrants a much longer discussion. Yeah,
this may be a good focus meeting for February.
Yeah,
particularly as the groups are not only going out for the spring, but also when they're up there at Marshall, James.
Yeah, I agree.
Okay. Any other questions on this topic? I mean, we are staying, we're a little bit behind, but we're staying pretty close to our schedule. So I think we'll have plenty of time for open discussion at the end as well. So if there's nothing else, we'll move on. Starting with our industry implementation presentations. We'll begin with Crately from Vigilant Aerospace Systems. Are you on, Crately?
Yes.
All right, you're good to go.
Hey, sorry about that. Oh, here we go. Okay. I was on mute there. Great. So my presentation here is really just to provide some updates and also some introduction for anyone who is new to what Vigilant Aerospace does. So I'll do a real quick intro here and then just talk about some projects and plans for 2023 and 2024 in the WINDMAP project. So Vigilant Aerospace provides our Flight Horizon system, which is an airspace management system. So our job and goal in this project is to become an endpoint for the collection, processing, and the display distribution of wind hazard information. So this is a product that does detect and avoid with multiple sensors for UAS pilots or for drone ports or UAS corridors. It's fully integrated with multiple sensors, so we use ground-based, and we've actually used onboard radars as well. There's a picture there of one of our projects, which we did for the FAA with an onboard radar, does situational awareness in a display, which you'll see some photos of, and does automatic collision avoidance. So it provides a command that is standards compliant to do collision avoidance between aircraft. And of course, as we add wind hazards, we will display those hazard environments as avoidance locations and provide an avoidance command. So it's really designed to help enable safe beyond visual line of sight flight. And that's going to be the focus of our involvement in this project in 2023 and 2024. Next slide. So this is what this system looks like in the field when it's being used in a portable environment. I also have some slides from it being used in a larger Air Force project right now, for example. But this is with OSU. We work with USRI on a lot of our testing. This is a member of Jamie's team here running a ground control station with a UAS in the air. We have the telemetry feed coming into our software so we can track ownership according to where it thinks it is at all times. We have ADS-BN, and then we have a portable radar. Increasingly, we also use live FAA data, really for higher altitude and controlled airspace environments, obviously, and a variety of other sources of data. On the right-hand side here, this is a picture of us using a fully onboard system. So it's all the same system, same technology, but running on a single board computer onboard the aircraft, onboard radar, and ADS-BN and autopilot integration. Next slide. So our goals for the 2023 and 2024 WINDMAP involvement would be development of a new concept of operations for beyond visual line of sight waiver applications, specifically to support research that USRI and other participants plan to conduct. This would include new UAS flights at higher altitude, so the ability to obtain waivers or COAs with a safety system that is providing automatic situational awareness and deconfliction, UAS flights into clouds. This will become obviously very important for this project. And then flights over longer distances and longer time periods to collect a much larger range of data. So we're excited about that. I'll be talking with Jamie primarily about that, but I know there are other opportunities and other flight campaigns that we would also like to discuss. So if you have one of those coming up, you think this would be at all useful, we'd be delighted to talk with you about that. Our goal is to assist, obviously, in safety and risk mitigation as a part of a waiver or COA to be able to fly these observation flights, collect this data, and then do detailed flight logging and data analysis. We have done this before. We've actually done this for NASA. There's a couple of projects I'll mention at the end of this presentation just over the last year where NASA has used our system. And we've done this for environmental observation where NASA will collect information about where either UAS or a crewed aircraft was located and then correlate that with other sampling. In some cases, it's been gas sampling for environmental observation or sound sampling for sonic boom observation to track exactly where an aircraft was located at the time that a sonic boom was received by a ground station, and then to do correlation across all that data. So NASA Armstrong particularly has used it for those purposes. Next slide. We did a demo day on December 2nd at OSU's USRI flight station. Really appreciate that and want to thank OSU again for that opportunity. We've done this a couple of times, and we have actually done a national DAA trial with MAP at Virginia Tech, and we've done extensive work with a quasi in Alaska. This was our demo day to show all of our newest features here in Oklahoma. It was a great opportunity. USRI flew 2 UAS for us to provide real encounters, and you can see on the lower left-hand side here some screenshots of those encounters taking place, the software automatically detecting that across multiple sensors and providing a real-time standards compliance avoidance maneuver for those 2 aircraft. Those 2 aircraft had an altitude offset, so the software was configured to trigger those warnings and commands, even though there was no actual danger of collision. So that's how we do these types of demonstrations and extensive testing. And so this was actually in the field, and it was fortunately not a bitterly cold day. So that was great. We'll probably be doing another one of those and certainly taking other opportunities to similarly integrate additional data sources as we move forward. Next slide. I'll just make you all aware we have an ongoing project with the U.S. Air Force. So we also work with larger UAS and use a variety of data sources. So we have data feeds coming in to track MQ-9 Reapers for the training command at the 49th Operating Group in New Mexico. They participated in the REMPAC maritime exercises for the first time this year with a couple of those Reapers. And so that was really exciting. But that's an ongoing project that we have going on right now with the Air Force. Just an example of the system being used with larger UAS. And this is really where WINDMAP results, I think, will have early impact is for this type of flight. And to be able to get that information into the system will be really important. Next slide. This is just some observations from the 49th Operating Group. They find that this type of situational awareness, data logging for training, and real-time traffic information is extremely useful, and they're working on integrating it into how they train and how they operate. Next slide. All right, so finally, just a few other updates. I know I've presented this system to this group before, so I haven't gone through all the details of it, but we have added some things over the last few months that I just want to highlight. One of those is that we have added the ability to have multiple radars directly feeding the system. We actually have projects in North Dakota where they are integrating multiple radars right now, and we'll be observing airspaces over specific cities from specific locations, and we'll be announcing that. We'll have more info on that as that project goes forward. That's really in support of a UAM style operation where the radars are located at a hospital helipad and are able to observe essentially most of the air traffic over a urban area. We have also begun scaling our system up. This is particularly in support of the Air Force, but also for other users, where we can track multiple ownships across an entire area and host it all in the cloud. So we're moving the data from the field to a cloud-based installation. This creates tremendous scalability and flexibility in the way that the system can be deployed. Another thing we've done, which I know the research engineers that we work with at USRI and elsewhere will appreciate, is that we now display mission planner waypoint files. So you can plan a flight and then display all of that and track it. And you can also simulate a flight and simulate encounters with your specific waypoints ahead of time. So we can set up a very aggressive encounter set where you're going to have random aircraft coming in and encountering your UAS, and watching the software respond to that, and then automatically take those avoidance maneuvers in simulation before you carry out your flight. So that's a brand new feature. I don't even think I've told Jamie or anybody else about that. And so we'll look forward to working with that feature for this sort of planning work. We've also integrated remote ID beacon tracking. This has come into play now with commercial UAS and small UAS are going to very quickly come with remote ID, or people will be adding remote ID beacons aftermarket. There's a lot of interest in that. We demonstrated that to the U.S. Army at their MEFX 23 demo a month ago. And we think that's really important for the future of commercial UAS all across the board. We also have the ability of pilots in our system to interact with UTM. This is something we've talked about before. This is not new, but we continue to add sophistication to those features. So you'll be able to take your mission planner waypoints, upload them as your reserved operating volume in the UTM system, and push that out through our system. So we're trying to make an end-to-end seamless, easy to use UTM system that goes all the way from initial mission planning to interaction with other third parties directly through the UTM system, with full visibility and flight horizon all the time across all of those, including real-time updates of where other aircraft are located from all the data sources that we integrate, and obviously collision warnings and avoidance maneuvers when needed. We're also displaying FAA en route data and adding additional FAA data and additional data rates. And some of you may have already seen that, but that is being improved and tested all the time. And we've also had two projects I'll just mention. One is the use of our Flight Horizon X system, which is a modification of our software specifically for tracking supersonic aircraft and spacecraft. This was developed at the behest of NASA Armstrong and Ricardo Ortega. We've used it specifically to track the supersonic testing of the new supersonic transponder standards on the F-18 test fleet with Armstrong. And then also this past year, and I think the paper, the IAA paper, is going to be one of those that's talked about in the next, presented probably in the next couple of weeks, integration to the ER-2 aircraft, the NASA research aircraft, which is the U-2. So that's pretty cool. That's been interesting. And those are just a couple of recent NASA projects. That's my presentation. Thanks, Jamie.
Oh, thank you greatly. Those are exciting updates. I did have a question on this one graphic that you showed here.
Yeah.
Can you give me a little more insight about what's happening with the urban modeling?
With urban modeling, so I think the project that is most related to urban flights and management of urban UAS is going to be around a hospital complex in a city in North Dakota. There's actually several projects like this that we're going to be working on. The one that is most advanced and that has multiple radars already installed, they're feeding our system, and we're working on calibrating and orienting all the radars literally over the next couple of weeks, and then beginning to enable some flights. And it's not this project. Just so you understand, the Air Force project, they're flying in mostly military airspace in New Mexico, which is what the 49th Operating Group does. So if you actually, well, if you go forward a slide, if you go to my kind of updates slide, I guess I don't have that in here, but what we're doing is we are beginning to develop data inputs using multiple radars, and then the ability to do our full detect and avoid and airspace visualization, tracking, and management in an urban environment. And specifically for a hospital, they have samples, biological samples they pull in from clinics, for example. They have things that they want to send out to clinics, and they really want to be able to do that via drone. And so that's the project that's being modeled here. So obviously being able to collect wind data in that environment will be very useful. And so that's something that we'll want to talk about in the near future. But that's the status. We're pretty early on that project, but it is one of the more sophisticated projects with multiple sensors in place, and eventually multiple users. And it's at a helipad. So there's
great. That sounds exciting.
There's traffic. Yeah. Any other questions? Happy to answer questions.
Greatly. This is James. I'm just curious. It'd be, I guess, the one question that popped into my mind during your talk was if you had wind information in your flight simulations, but then also toward the end when we talked about the urban landscape area and your support for the flights, providing sort of high resolution wind information could be of value and something that we'd be interested in working with you on.
Yeah, happy to talk about that. The stage of those types of projects is really in development of air traffic surveillance initially, and that's the highest priority right now. And then the ability to begin to add these other types of data sources, collecting wind data as either crewed aircraft or uncrewed aircraft enter and leave that space would be very, very interesting. So
yeah, it'd be interesting from a data simulation side of things, and also from a sort of a high resolution model validation side of things.
Yeah, and as we get further along with that project, James, we as I say, I have sort of 2 to 3 projects that look a little bit like this. Mm-hmm. It's people who are developing essentially drone ports. They tend to either be, some of them are rural, so a lot of the work obviously that we do is rural, but some of it is more suburban. This would really be classified as suburban. It's not a very high density city, but it's very much an urban environment. And then some of the other work we're doing is in much higher density urban environments. But it's really about collecting the air traffic surveillance data and really establishing that safety case. And then being able to add sensors to routine aircraft that are being used that can, fly ahead and essentially be carrying out their daily mission and collecting this wind data and providing it to you all, is obviously potentially very interesting. So, yeah.
Thanks greatly. It's really exciting to see the addition, especially the mission planner capability. I wanted to understand, maybe I missed something here. Similar question. Is the simulation a built-in portion of this? Is it an extensible, interface that people can be interacting with? And how would we go about sort of incorporating that? I just want to understand the simulation capability a bit more.
Yeah. So our simulation capabilities are primarily intended to demonstrate the effectiveness and performance of the avoidance commands. Right. So that's really why we have simulation in our system, is so that we can pre-validate and run, hundreds of scenarios around a particular encounter set, and then demonstrate that the system is providing the right avoidance commands. So we do have the capability of uploading a series of waypoints, or uploading a specific set of flights and encounters that you want to simulate. We have not built in, for example, the ability to simulate weather or the impact of weather on a flight. That's really kind of to the side of what we typically are focused on, because we're a safety company, right? So it's collision avoidance is number one. Enabling this type of research with collision avoidance capabilities, for example, is our primary role. And then being able to show in our simulated environment, and then potentially having additional data sources like a wind hazard area in our simulated environment to show how you would avoid that, is certainly something we'd be very interested in doing. But we do not have specific weather or wind data simulation capabilities. Happy to integrate with other people that do, and or pull data in or push data out. But that isn't a primary function of the software.
Okay. So, I mean, is the best way to, if somebody wanted to integrate that at, atmospheric physics, or it sounds like you're probably doing kinematic projection, flight dynamics. I mean,
only to a very limited degree. Keep in mind that collision avoidance is on the, the multiple meters to quarter of a kilometer kind of range, right? So you're really just tracking the aircraft with precision GPS, but the aircraft getting blown around, it may be a hazard to the aircraft, it may be a hazard to people or things on the ground as a safety hazard for the aircraft, but it is not usually a hazard in terms of collision with other aircraft, because the distance you're required to maintain from other aircraft is large, right? So that's just a dynamic of the way that the part of the safety case that we address.
Right.
Yeah,
I understand.
That's all.
Okay.
Yeah, but we're happy to pull data. Yeah.
I think what I'm trying to understand is that, if somebody wanted to integrate more capability or some, more reactive, is that something we'd work with you to integrate, or is that something that, there's like an API that we should be interfacing with?
We can do that, and we pull in data. We pull in data from a wide variety of sources, and we've architected our software so we can do that really quickly. So, the short story is, if you want to, our goal, the way that we imagine this working, is that we will have a stream of data that is describing hazardous areas, and that we translate that into essentially a hazard or an obstacle in our software, which is really what our software is designed to do. And then we'll provide avoidance around that hazardous area. So in terms of simulation, if you were, for example, to give us a file or even stream data to us, we could then simulate flights through those hazards and how we would avoid those hazards. We could absolutely do that.
Thank you.
Okay. Hopefully I'm answering the question, but I'm happy to talk with you about it further offline.
Yes, thanks.
Greatly appreciate that. Thank you. So we'll go ahead and move on to Apoorva.
Hi, folks. Can you hear me?
Yes, you're good.
Okay, this is Apoorva Bajaj, and I'm with Climovation. Just to set the background a little bit over here, we're a startup. We're in the weather services provision space. And one of the areas that, we're looking to do work in is provide weather hazard information to different operators and to folks like Prately who are, providing systems out to air traffic management ultimately. And our focus is in two different areas. One is improving our ground observations, lower boundary layer observations of weather information in parts of the country that don't have great observations, and current focus is on weather radars and filling in what are known as radar gaps in the country where you don't have a lot of good information close to the ground. And then the second piece is taking those observations along with other unique observations that, are being developed as part of this project as well, and integrating that into our modeling work at the company as well, so that we can improve our forecast models as well. And that allows us to provide all of this type of improved information, not just within the drones and AM space, but also to other industries. So that's a quick background on the company. Since we've last spoken here and presented here, I wanted to give an update on the deployment of weather radars. So we are looking at deploying about 200 weather radars across the country in the next 4 years. That process has already started. We're about 6 radars in right now, 2 in North Carolina, 1 in Georgia, 1 in Louisiana, 2 in Texas. A third one is going up in North Carolina this month. And then for the rest of the year, we're deploying about 2 weather radars every month through the rest of the year. So we should have about 35 radars deployed by the end of the year. What I did over here in this slide is looked at some of the states that, some of the folks from this call are on, in order to just let you know the different parts of the country where we're actively putting radars in, so that we can find opportunities to collaborate. And I think a lot of opportunities came up as I reviewed the conversations today for the use of weather radar data, whether it's to see where convective initiation actually took place, whether it's the tracking of wind hazards, and then finally, integration into assimilation models. So what does having more low-level coverage in rural parts of the country where you don't have coverage do to the weather prediction models ultimately? How does it improve the assimilation? So these maps over here just quickly show you for Oklahoma, Kentucky, and Nebraska. The blue and the purple circles show the different locations where we'll be deploying radars over the next few years. In Oklahoma in particular, at least 4 radars will be going up this year. So there's an interesting overlap here with the work going on in Oklahoma State and Choctaw Nation. And I just wanted to show you the map of the tentative locations and timing for the installation of those radars. And hopefully, they'll be deployed soon and we can coordinate on some efforts there. But you can also see radars in Kentucky, especially where University of Kentucky is doing its operations. And then I just wanted to present a picture for out in Nebraska. This will be probably a year or 2 away, but we are also putting up radars in Nebraska as well. I looked at maps in Virginia as well. I don't think there's a good overlap with the radars that we're deploying in that region because, I think the locations where you have test sites have good coverage from the existing NextRad radars. Next slide, Jim. And you can play that first loop, any one of those.
Yeah, it looks like we're having a problem with the media.
All right, no worries. No worries. So I'll just talk through the two videos that I was hoping to show over here. I just wanted to let you know that these radars are up and running, and these are some observations from North Carolina and from Georgia. The first video was meant to show basically we're already starting to develop rain rate information, which is something that is of interest to advance air mobility. We've heard from a lot of operators that having precise information on rain rate is very valuable in terms of certification and validation activities, because there's certain rain rates at which they cannot fly anymore. And those rain rates are much lower in value than, you worry about when it comes to flooding type activities. So we have implemented some initial rain rate estimation algorithms on the data coming out of our radars now, and then we are making them more sophisticated. The image at the bottom, it was supposed to be, again, a video of Hurricane Ian. And what that imagery basically shows on the left-hand side was what the data collected by the NEXRAD radar. And on the right side, it shows data collected by our radar. But if that video had looped through, what we saw with doing low-level radar coverage of Hurricane Ian as it moved through the area is that once you get, once the hurricane was no longer visible on the NEXRAD radar, we were still seeing a lot of rain close to the ground. And that's typical of hurricanes where there's a big gradient in the rain observations close to the ground. So in fact, if you were doing some sort of search and rescue operation following a hurricane event, the NEXRAD imagery would have implied that, there's no more rain and it's safe to fly. Whereas the low-level observations that we were taking showed actually, this is the Winston-Salem area, that there was a lot of rain on the ground for at least 15, 20 minutes after the NEXRAD radars were showing any rain. And then the last thing over here on this slide, on the image on the left, we just captured a tornado in Georgia. And it also starts giving you a picture of, the high resolution imagery coming out of these radars. Those are county boundaries that you see over there. They haven't yet, they're still doing their damage surveys to determine the type of tornado it was, but it's probably an EF0 or EF1, and it showed up in very high resolution in the imagery that we're capturing. So that's all I had to present today. I just wanted to update folks on the status of our radars, that they're deployed. They're starting to get deployed. They're coming in the areas where we're doing these campaigns in WINDMAP, and maybe put into place, and this is part of the campaign discussion, I think, ideas for how you can take in the data from the radars that we're deploying and integrating them into your models and, the different solutions that you're developing. So that's all from me. Happy to take questions.
Excellent. Thanks, Apoorva. Very timely. So questions for Apoorva?
Keith.
Yeah, thanks, Apoorva. Good to see you last week in EMS. On the radars, is there a distribution and sharing policy, and how would, for this academic project, are you willing to share the data?
Yeah, for WINDMAP, we'll make the data available to the participants on this call for analysis and for contributing towards the results of this. If in future proposals we can talk about some like reimbursement for the integration services, but for WINDMAP we're happy to support.
So you're going to have an API or put them on the cloud or something?
Yeah, so as you can imagine, since we're deploying these 200 radars, we're building a pretty big tech stack at the back end to manage the real-time distribution of all of this data going all the way out to the weather service offices. So we're basically going to be leveraging that same API that we're building and data feeds that we're building for provision to anyone on the academic side as well. I think there'll be a lot of interest in just archive data in this case. So, building that database so you can go in and grab files on your own. Initially, it'll probably be, give me the data files from this date to this date, in this format, and they'll be probably manually served initially.
Okay. Thanks.
Yep.
Any other questions for Apoorva?
Yeah, just a quick one. This is pretty simple. I may have missed it along the way. What is this, an S band, C band? What's the frequency of these?
Sure. So we're operating these radars at X band.
Oh, these are X band. Okay.
So it's a high frequency radar, but it allows us to get very high resolution information, both on rain rates and then, the development of the storm structure. And I think that high resolution is really the driver for going to X band, among other reasons. S and C band in particular also suffers from interference issues more and more with the telecommunication industry. So it moves to, there's benefit to going to X band. And each radar has about 60 mile or 100-kilometer radius with these radars. So you don't get as much range as the S band radars. But you do get coverage over rural locations, which will be important for all the regional air mobility applications.
Yep. Thanks.
Yep.
This is a pretty basic question, but when you say low altitude, are you going from like 0.2 degree inclination to 0.1? And then what is your sort of update rate?
Yeah, so we're looking at about 0.5 to 4 degrees or so. So the lowest beam there will often see observations all the way from 500 to 1,000 feet off the ground, even closer as you get in closer towards the radar. But the goal is not to have volumetric observations, because you do have observations aloft from nearby or distant next-rad radars.
Okay,
so about 4 tilts in, the 4 lowest tilts that you can get.
Thank you.
All right. Thanks again. I really appreciate it.
Yep.
We had an updated presentation from the Choctaw Nation. So Mark, if you're on, go ahead and let you take control.
Yeah. So it's just a couple small updates. So as we're going forward with getting approvals for BV loss using our tactical mitigations instead of visual observers, we've kind of got this plan laid out. We are, we are a little over 5 months in on our initial BV loss without VOs submission for that flight area there at White and Yellow. It's 7.7 nautical miles by 4.4. That's just up to 400 feet, but that's kind of our first phase towards working into the clouds. We were a couple RFIs in, and we finally got the FAA waiver team happy with our DAA solution using ground-based S-band radar and ground-based ADS-B, doing all of our detection with ground-based with a secondary operator as a kind of an airspace observer. But anyways, had a final meeting with them last week, and we're any day now for approval on that. So that's our towards in the clouds, our crawl. Then we're moving to walk. We already have Part 107 altitude waivers up to 2,500 feet, but we're going to combine those two waivers. Ideally, that submission is going to happen March 1st, and get the FAA to hopefully approve 2,500 feet BV loss. Then getting them comfortable with us using those DAA solutions up to altitude, and that's going to get us running into hopefully the into clouds. Initially we were trying to go for airframe platform agnostic. They they didn't like that. So our initial platform I've got pictured there is one of our VTOL fixed wings. That's kind of our initial vehicle that we're going to be using under that. So that's our timeline. March 1st submission for that other BVLOS with, we can currently, do simulated, into cloud missions, but that final into clouds is going to, its timeline is going to be based upon the approval of that second. So I don't have a hard date for that yet, but that is, hopefully still this year. If you can go to the next slide. So we also, some of the things that we've done to grow our capabilities, we've got the capability now to do remote unattended operations. We've acquired 4 of the Skydio X2E with the outdoor dock system, and those can be operated with no personnel on site. They're we can from anywhere in the world get on computer and launch and recover the aircraft. We can currently operate that up to 2,500 feet using a VO on site, but with the RPIC off site. It's we're ready to probably work with Jamie to get weather instrumentation package integrated onto the aircraft. But we also are, in conjunction with those other waivers, going to work towards a waiver for this with the ultimate goal of completely unattended remote operations with just scheduled flights with everything autonomous. No, the long-term goal on that would be no RPIC and automation, detecting and avoiding. That's probably a ways off. And then we're also, if you can go to the next slide, we're this is more for our testing site capabilities, but we are kind of growing our weather monitoring instrumentation. We've ordered a CL61 ceilometer that should be in early to mid February, and we're just about to purchase the Visala Wind Cube, which from I think it's got a 300 meter range for like detecting wind speed and direction, and among other things from the ground. So that's just a quick update from CNO. Anyone have any questions for us?
Mark, thanks for sharing. What was the big driver on choosing Skydio as your provider?
So we had shopped around with a few different systems, and that boiled down to one of the driving factors was cost, as well as we already had a pretty good working relationship with Skydio, and their collision avoidance technology was another. Now it's not collision avoidance in the sense of DAA for like a manned aircraft intruder, but as far as avoiding stationary obstacles, it's not obviously the best platform for integration. They have a dedicated payload bay, and it can provide about I think 15 watts of power to an external sensor package, but we are also in talks with them about pulling off. They currently collect temperature, pressure. They don't collect humidity, and they should be able to. And I guess it does compute wind speed, as it's for holding position, but we're in talks with them about getting that data to be able to be live exported from the aircraft, to actually get that information directly from the aircraft itself. But I would say kind of cost and having a good working relationship with them was the largest driving factors to Skydio.
Yeah, and I think that'd be a good place to start, maybe in terms of comparing that with some of our calibrated systems.
Mm-hmm.
This is James. Nice presentation. I'm curious. How often can it be launched and recovered? I guess how long does it take to recharge?
And so they have about a 35-minute flight time, and so we just got them installed this week, and we've only put about 2 hours of flight time on it. But it was, from what I could see, an hour to an hour and a half to go from a depleted battery back up to full.
Ah, okay. And I'm curious how robust it is at being able to land on that. It seems like a very tiny little.
It's pretty impressive. So the wind was sustained 10 to 15, gusting up to 20, and it made it home to its dock.
Wow.
It seemed like the biggest limitations were actually early morning and late evening flights, because it's all vision based when it gets down there, and it's looking for a QR code and thing, and a number on the top of the dock. And when shadows are covering that was problematic.
It's interesting. You think you'd be able to solve that pretty easily with some external lighting.
Yeah, and that is one that they have external lighting on the top to help illuminate that, but we're in their early access program, so it's not, I guess, a publicly available product yet, only for their early access. So they're still early in development and getting frequent updates. So, but we are going to be exploring using fixed lighting at our site to improve that, as well as other things.
Can I ask how much one of these systems costs?
So the breakdown of hardware versus like software licenses. I think the hardware cost on the dock was around 40,000 a dock, and the aircraft around 10,000 an aircraft. And then there is, for their Skydio cloud, I think a few thousand a year per system.
The software or the storage or
yeah, and there's it records everything and saves to their cloud, and so everything's auto as soon as it lands. Everything's now, of course, video is not as important for weather collection, but it saves all of that video, it uploads it and saves it to their cloud while it's in its recharging period.
Wow, really interesting. Thanks.
Okay, great capabilities. Look forward to moving forward with that. We did get our WinCube up and running last week, Mark, so we can start doing some discussions about how we want to collaborate on that as well. Okay, so with that, we're going to do a very short outreach presentation. So this is an opportunity for us to highlight some of the various outreach efforts that have been going on. Obviously, you've been working very closely with the Choctaw Nation on this site, but Imran has been developing some stuff that might be useful for some other outreach activities. And if you have other stuff in the future you'd like to highlight, just let me know. So Imran, I'll go ahead and let you take it away with this.
Thanks, Jamie. So what the item is the Seascape, or Simple Educational Autopilot with C++ architecture and Python exterior. And so the first question you have to answer is, why another autopilot? I mean, the field is full of lots of autopilots. And one of the things that we were working to address is the fact that for new entrants to the field, those autopilots can often be somewhat intimidating to integrate with. And they're not always open access. Sometimes once we reverse engineer an open access tool, the vendor makes that closed again, and those sorts of things. And if we look at some of the open access tools, something like Autopilot has 50,000 lines of code and a hardware abstraction layer, and for a lot of engineers that can be intimidating as well. And it's so yes, while there is a lot of really great built-in capability, we saw a need for a really minimalist autopilot that an engineer could really easily understand and interact with, and something that they could use Python or some other kind of relatively easy language to pick up. And so we really aligned it with our our undergraduate coursework that teaches things like Python. We aligned it with using single board computers so that they'll students can really wrap their heads around this just being a flying computer that has some additional peripherals. And so if you'll go to the next slide. Just a little bit on the architecture. The architecture really kind of mirrors the traditional sort of GNC class. And so the GNC split, we've sort of hidden all of the drivers. They're written in C++. You can certainly see them, but we've tried to make them more or less transparent. And then we've basically given a shell into which somebody can write a controller or an estimator and really just switch them out. So we paired this with a graduate course. And the first time we taught this, the workload was actually fairly high because we were really addressing every element of the GNC pipeline. And so since then, what we've done is we've kind of scaled back, and the students are provided with an estimator, a baseline estimator. They have the opportunity to design their own, but they can basically flip on or off any of these functions so that they can test their own custom controller, but with a existing estimator, or vice versa, or waypoint planner. They can basically drop in and pull out their different functions, and those will be in Python. The system works with a shared memory addressing under the hood, so it's faster than the original Python implementation. In other words, we're not seeing the big performance decrement, especially when they're just testing one function. So we went ahead and recoded a lot of things under the hood. Next slide, please. So we'll have a talk on this at SciTech, just on some of the educational outcomes. Here are some examples of, this fall, a couple of flight tests, and you can see those smiles. Those are people that have just flown their first autopilot that they designed from theory, and there's nothing that replaces sort of those smiles. The top right is actually an example of an educational experience. This team designed an autopilot, however, they made a sign error, and so they got their axes flipped, and so the autopilot flipped the airplane upside down and flew it beautifully upside down, and continued to fly the airplane upside down for several seconds. You see here. So in that sense, their autopilot did work, but they had a sign error in there, and they learned a lot from that. And we've had a lot of feedback that yes, the course was fairly intensive. But as far as the learning outcomes and the confidence has been great. So I think that's everything. Thanks.
Well, my first comment on this is, I'm a traditionalist, and I think your first experience with an autopilot should result in tears and not smiles.
This is their first successful experience. There probably
So
were some tears.
There were tears leading up to it.
Probably, yes. Blood, sweat, tears.
Great work. Do we have any questions or comments for Imran? All right, thanks. So we'll be following up with this, and for those that are interested in, integrating this into outreach or coursework, this will be something that we'll be starting to, populate the website to be able to share some of these resources more publicly that have been coming out of the project. Okay, thank you again. So that brings us to our final topic for the day. I know that we're already over noon, so we'll try to keep this as brief as possible. But these are, fairly important discussions for us to have as we start planning for the coming spring. And so, if we think about where we had hoped to be last year, one of our goals on the stretch side in 2022 was being able to do in-cloud flights, the Choctaw Nation, and we still haven't gotten there yet, but we're getting closer. So I don't know if Mark wants to talk about those discussions anymore, but that is still progressing with the mitigation systems that they currently have at Daisy Ranch. And then we will have, actually, I think, Gus, I have your slides here in a minute, so we'll talk about your plans for Marshall in just a second. So I thought I'd give this an opportunity for the different groups to discuss upcoming plans for the spring and then stretching into summer. But obviously, in our later spring meetings, we'll also be talking about what our summer plans would be. So with this, I think I'll go ahead and start. with the order that I currently have in the deck and let Gus start off with their visit to the Marshall site and the goal they're in.
Right. Thanks, Jamie. So as Apoorva presented here earlier, we do have considerable data gaps in terms of weather near the ground. And this causes all sorts of problems, not only for actual operations, but even if you're trying to plan a flight around forecasts and models. So in 2018, started looking at this. I was part of the team that started looking at this with Daniel Tripp and Heather Reeves, looking at the differences between models and observations aloft and the observations on the ground, and trying to map this this gap area in terms of freezing layers and melting layers to understand why particular winter precipitation was changing and what was happening in terms of melting, refreezing, and particle sizes, and why they didn't match the expected. In a sense, to enhance this modeling and forecasting ability. If you could go to the next one, please, Jay. And so, as a continuation of that work right now, we're developing a new sensor payload to enhance those measurements. And as many of you here are familiar, we do have in-cloud observation limitations from the FAA. And so we were working with a payload that could do the vertical profiles we were doing, but then extend the measurements into the cloud region with remote sensing. In particular with the phased array radar on board the aircraft. But as this work and this discussion started happening, I guess in great part because of the advances of groups like ours and NASA that is really pouring gas in this fire, right? The beyond line of sight and the advanced air mobility side of things are really pushing these scenarios. And besides the need to understand and better forecast this close to the ground region, not only for flight but also for hazards on the ground as well. But because this is such a fast growing area, it is just so that the groups like ours are forcing the hand, in a sense, of regulations, right? And so now the FAA is actually running to try to keep up with the demands, and they're now looking into how they can even certify these beyond line of sight systems to encounter these kinds of weather, avoid these kinds of weather, and even in terms of aviation alone, if they can withstand these types of freezing conditions, right? And so if you go to the next one, Jamie, please. And so for this reason, it may be that soon we'll have this permission for in-cloud measurements, and so that we can start answering these questions, right? And so we're working to, besides the phased array radar, to look into particle size distribution with the optical particle counter, and also looking at liquid water content with a probe, which is great synergy within our group, because I definitely will talk to Sean about even how we are currently trying to validate these measurements. And James actually gave Sean and I both a great idea on even how to work the scales, because in our case, the OPC is actually doing measurements from 0.41 microns to about, I think, 37, if I'm not mistaken. And then with that, we have the radar for the larger particles such as snow, rain, and things above the 3.7 millimeter size, right? And so to to first take a crack at this work, there's actually two parts, right? Because as Jamie pointed out early in this meeting, there's the observation part and the development of the sensors that allow this to observe the weather so that we can learn more and be better at forecasting and predicting what's happening here. But there's now a second part, which is what kind of low-cost technologies can we have and put on these aircraft that are doing long-range missions that they can see and avoid weather, right? And so if we could go to the next slide, please, Jamie. Alyssa, Avery, and I are working with folks at NCAR and the FAA to do a flight campaign at Marshall Field, which is a NCAR facility at the foothills of the Mesa Laboratory, which is a really, really interesting site to do this, because as James presented earlier, not only there are a great number of instruments there that we can compare our measurements to, such as present weather sensors, the towers, the astrometers, all sorts of ground-based instruments, but also they have a vertical pointing ground-based radar that we can compare to our radar that's flying. And the interesting thing is that our radar, because it's in the millimeter wave range, right? We're talking about here 77 to 81 gigahertz, so W band. We can create these really high, really high resolutions. We're talking about within a range of 20 meters near the aircraft, we can look at 0.1 meter range gate resolution, but within a 250 range meter away from the aircraft, we're still looking at half a meter range gate resolution. And so we're really excited about this campaign coming up in March to test the system and see how it's going to behave, in particular to try to target scenarios that are, even when you have good radar coverage or even satellite coverage, you're not really picking up just because of the fine scales of the phenomena, such as freezing drizzle and smaller particle winter weather precipitation. And so we're really excited to do this. And we're also have two points of synergy, both within the group and outside of the group. As of today, we have a meeting with Crately later today to discuss how to do these in-cloud measurements safely and potentially use their systems to help us create a concept of operation that would make the FAA comfortable in approving this kind of operation, which would set an amazing precedent that even though the Choctaw is working on having a continuous permission to do this right now, even as Mark often says in the crawl, walk, run fashion, to have even a punctual operation of 1 week permission to do this would be really good in terms of setting the precedent. Because as the FAA moves on to 2024 and they start working on certifying UAS for winter weather flights, they will also need to know if even the certification flights were in the conditions where something actually could have happened to the aircraft. So to determine if the aircraft survived winter weather conditions, you first need to determine if the aircraft even flew through winter weather conditions, right? And so this is really important work. And another point that I wanted to highlight here is that besides the science portion of this field campaign, the site is also very interesting because, as you can see the sectional charts there, it's a even though it's not an urban area, it's a area between urban centers, medium and large. Denver's not too far away from that location. And so you have a series of airports and a lot of traffic from hospital and helicopters near the area. So the ability to demonstrate there we are operating in such a crowded airspace and provide valuable weather insight in a region that does have very interesting weather near the ground that could affect not only the UAS operations, but even the airports nearby and hospital heliports. It's going to be very, very important for future work in terms of creating precedent and showing the maturity of the technology of safe operations. And so we're really excited, not only for the science, but also for the signal that this puts out of our community in terms of operations.
Great. Thank you very much, Gus. Really appreciate it. So I think it should be some really interesting results that come out of this. So do we have any questions for Gus on this? All right, we'll keep the team posted as we move forward with the plans. Obviously, we'll be working very closely with James and the rest of the NCAR team to make this happen. All right, thank you for the update, Gus. I don't think we need to talk any more about this since Mark gave a really good update on where things are going with the BV loss testing at Choctaw Nation. These are kind of our timelines for what we'd like to be able to achieve with this coming in the spring. Hopefully being able to do cloud tests, sometime late spring, early summer timeframe. So Mark, I don't know if there's anything additional that you'd like to add on where things stand right now.
No, just if anyone else has any more questions, I could try to answer them the best I could.
Awesome. Thanks, Mark. And we'll keep everyone posted in future meetings as we move forward with these plans. And I have an additional slide. Sean, I don't know if you want to talk any more about what you're doing in the mountain testing.
Sure, Jamie. Very quickly, we got a extended line of sight waiver to fly over the mountains, so we can get about 3 miles out and back. So we're going to plan for that this spring. We'll try and do several flights, measuring the winds and turbulence and pressure, temperature, humidity over those, looking at surface roughness effects on momentum transport. And we'll also be doing vertical profiles at our launch site simultaneously, so we'll be able to do a comparison on that end. Other than that, please keep us in touch with about the cloud flights. In cloud flights, we'll be moving forward with our sensors, so hopefully we can participate in that. So I don't know if it's best for us to bring our aircraft there, but it sounds like we actually need to have.
Yeah, I think that's probably the best approach, but we'll keep everyone posted as things move forward on that.
Yeah, we'd be using the same aircraft we used for the extended line of sight waiver. So if there's paperwork you need, we'll have. Thanks.
Hey, Sean, real quick, does your extended line of sight waiver require a VO?
Yeah.
Okay. Thanks.
That's the extended part.
Yep.
And I didn't add anything in here in FogMap, Sean, since that's not a direct WINDMAP program, but I don't know if you want to save that for another time, maybe on, some of the results coming out of that, because there's very interesting stuff going on.
Yeah, we fed everything to James, so I think we're kind of waiting for the feedback from the
good. Okay. All right. Final comment on ours. I showed this a little bit earlier, so I'll just make a quick comment on this. We are doing some what we call simulated urban testing here, using some of our high-rise dorm facilities to be able to situationalize and get trained on operating the aircraft in a building environment. So we've currently primarily done this with single vehicles to date at different locations around the sites, and we're moving up to using coordinated swarms of vehicles to be able to do simultaneous profiles. I think the biggest thing, that we've taken away from this in terms of the lesson is being able to, stay on station long enough to get plenty of statistics due to the large variability that we see around the buildings, and having multiple simultaneous measurements is going to be really critical for this to be able to get a better understanding of what's going on. The goal with this as we move forward is to then go back to that potential urban profiling. And again, we're looking at, the Oklahoma City region. In this, we have a lot of questions that we need to answer on how this is going to move forward, both in terms of where we're going to be siting some of the ground assets with the various LiDARs, and where we're going to be doing flights at with the UAS. So we've currently only been doing flights around our USRI facility located over here. But we're looking at various locations, particularly around the Devon Tower, that will work ideal for these in terms of both the ground stations as well as the aerial flight. So this will be moving forward in the spring. So we'll be able to provide some additional updates on this as we go through the planning process. So with that, we'll have open discussion at this stage. Certainly, any questions or comments from any of the WINDMAP team members, but also like to have the opportunity for any of our guests or BOA members that are on the call today to be able to answer or ask questions as well.